Good evening and welcome to Physic for Sleep. Tonight we embark on an intellectual journey exploring one of the most profound questions of our time. Could aliens exist? A scientific breakdown of the Fermi Paradox. Before we gently immerse ourselves in the vast silence and profound questions of the cosmos, I would like to know where you are at this moment. Perhaps you are sitting by a window, watching the soft rhythm of the falling rain. Or maybe you are nestled on a quiet garden bench, observing the subtle dance of shadows as twilight deepens. If these deep reflections help you relax and organize your thoughts before sleep, please support the channel with a like and subscribe so others can find their way here too. Now, just breathe, allow your eyes to grow heavy, and let's begin. Our journey into gravity begins, as so many profound scientific narratives do, with a story. It is a tale often told of a falling apple and a brilliant mind named Isaac Newton. In the late 1600s, Newton, a contemplative scholar, observed the seemingly simple act of an apple descending from a tree. And in that moment, a profound realization blossomed. He did not merely see an apple falling, he saw the same fundamental force that governed the celestial dance of the moon around the earth and the planets around the sun. Before Newton, the heavens and the earth were often considered separate realms, governed by different rules. Terrestrial physics described falling objects and friction, while celestial mechanics dealt with the perfect, unblemished motions of astronomical bodies. Newton, however, dared to unify these domains under a single, elegant law. He proposed that the very same pull that brought the apple to the ground was responsible for keeping the moon in its orbit, preventing it from hurtling off into the void. This was a radical departure, a conceptual bridge spanning the vast chasm between the earthly and the cosmic, inviting us to see the universe as a coherent, interconnected system. Newton's universal law of gravitation posited that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This mathematical relationship, profound in its simplicity, allowed for precise predictions. Imagine two celestial bodies, perhaps a star and a planet. The greater their individual masses, the stronger the gravitational embrace between them. Conversely, the farther apart they are, the weaker this force becomes, diminishing rapidly with the square of the separation. So, if the distance between two objects were to double, the gravitational force between them would reduce not by half, but by a quarter. This inverse square law is a cornerstone of our understanding of how forces propagate through space, a pattern that reappears in other fundamental interactions, such as electromagnetism. It describes a universe where mass itself is a source of attraction, drawing everything toward everything else in a silent, ceaseless ballet, a cosmic waltz orchestrated by an unseen force. The elegance of Newton's law was immediately apparent in its ability to explain phenomena that had long perplexed humanity. It provided the mathematical framework for Johannes Kepler's empirical laws of planetary motion, showing why planets orbit in ellipses rather than perfect circles, and how their speed varies as they approach or recede from the sun. It explained the ebb and flow of tides, attributing them to the gravitational pull of the moon and, to a lesser extent, the sun on Earth's oceans. Even more remarkably, Newton's theory allowed astronomers to predict the existence of unseen celestial bodies. When Uranus was observed to deviate slightly from its predicted orbit, rather than abandoning Newton's law, scientists, notably Urbain Le Verrier and John Couch Adams, hypothesized the gravitational influence of another, as yet undiscovered planet. This led to the triumphant discovery of Neptune in 1846. A testament to the predictive power and profound accuracy of Newtonian gravity. This was not merely a description of what was seen, but a powerful tool for unveiling the hidden architecture of our solar system, affirming the power of human intellect to unravel secrets. Yet, despite its immense success, Newton's theory presented a fundamental mystery that even he found deeply troubling: the nature of gravity itself. His equations described how gravity acted, but not why or what it was. It was an action at a distance, an invisible instantaneous pull that traversed the vast emptiness of space without any apparent medium or mechanism. How could one body instantly influence another, millions of miles away, without anything tangible connecting them? Newton himself acknowledged this profound philosophical puzzle, admitting he could not explain how such a force could operate without any intervening medium. He famously wrote, "I feign no hypotheses," meaning he would not speculate on the underlying cause, content to describe the observable effects. This mystery lingered for centuries, a silent question mark at the heart of classical physics. It was as if the universe operated through a magnificent yet unexplained enchantment, where masses simply knew how to attract each other across unimaginable gulfs, a form of cosmic telepathy without a discernible channel. This conceptual void, this lack of a mediating mechanism for gravity, became an increasingly prominent point of contemplation as scientific understanding progressed. While Newton's framework was undeniably effective for most everyday phenomena and even for most astronomical calculations within our solar system, the absence of an explanation for its fundamental nature left a lingering sense of incompleteness. It challenged the very notion of cause and effect as understood through physical contact, implying a form of instantaneous communication that seemed to defy the very limits of physical interaction, especially when considering the finite speed of light. For many, the idea of an invisible force reaching out across the cosmos, pulling and shaping without any tangible connection, felt akin to a magical influence rather than a truly physical one. And so, while we could calculate the precise trajectory of a comet or the gravitational field of a distant star, the essence of the force remained elusive, a profound enigma tucked within the very fabric of our physical reality, hinting at deeper layers yet to be uncovered. Consider for a moment the profound implications of this invisible connection. Every object around you, every book, every chair, even your own body, is exerting a minute gravitational pull on every other object, on every atom in the room, and indeed, on every distant star. Though imperceptibly weak on our everyday scale, it is this universal attraction that binds galaxies, forms stars, and keeps our feet firmly planted on the Earth. It is the silent, ubiquitous architect of cosmic structure, a force that connects the smallest pebble to the grandest nebula. When you feel the weight of your own body or observe the gentle sway of a pendulum, you're experiencing a direct manifestation of this ancient, invisible force, first articulated in its mathematical glory by Newton. It is a constant reminder that we are not isolated beings, but integral parts of a vast, interconnected cosmic tapestry held together by the very same threads that bind the planets and the stars. This deep, pervasive connection, though mysterious in its origin, offers a quiet sense of belonging within the grand design, weaving us into the grand narrative of the cosmos. The enduring legacy of Newton's work is not merely in its mathematical precision, but in its profound shift in perspective. It revealed a universe that was governed by universal laws, comprehensible through observation and reason. It paved the way for future scientific inquiry by establishing a framework where physical phenomena, whether on Earth or in the heavens, could be understood through a consistent set of principles. It instilled a confidence in the human capacity to decipher the cosmos, transforming speculation into prediction and mystery into measurable reality. For over 2 centuries, Newton's gravitational theory stood as the unchallenged cornerstone of physics, a testament to his extraordinary insight. It was a golden age of mechanics, where the universe could be seen as a grand, predictable clockwork mechanism, set into motion by divine decree, but running according to immutable, discoverable laws. The universe, through Newton's eyes, was a place of ordered beauty, where every motion, from the smallest falling leaf to the grandest planetary orbit, obeyed a single, unifying principle, inspiring a profound sense of intellectual peace and harmony. And yet, As with all great scientific revolutions, the very success of Newton's paradigm eventually gave rise to new questions, new observations that his elegant framework could not fully accommodate. The instantaneous action at a distance, while mathematically convenient, remained a conceptual stumbling block, especially in the context of emerging ideas about the finite speed of light. Furthermore, as the precision of astronomical measurements increased, subtle discrepancies began to emerge. The orbit of Mercury, for instance, exhibited a tiny precession around the Sun that could not be fully explained by Newtonian gravity, even after accounting for the gravitational tugs of all other known planets. These minute deviations, though initially dismissed as observational errors or accounted for with ad hoc hypotheses, slowly began to accumulate, hinting that perhaps despite its immense power, Newton's description of gravity was not the final word. It was a whisper from the cosmos, suggesting a deeper, more intricate reality waiting to be unveiled. A reality where gravity might be far more than a simple pull between masses, but an intrinsic property of the very stage upon which the cosmic drama unfolds. This quiet unease, born from the very triumphs of scientific rigor, would eventually pave the way for a revolutionary new vision of gravity. The unresolved questions surrounding Newton's majestic framework began to coalesce into a whisper of deeper truths, particularly the perplexing notion of action at a distance. How could the Sun, some 150 million kilometers away, exert an instantaneous pull on Earth without any intermediary? This seemed to contradict the very nature of physical interaction, suggesting a cosmic connection that defied all known mechanisms. It was into this intellectual landscape that a young patent clerk named Albert Einstein stepped, and in 1905 he unveiled his theory of special relativity, which, though not directly about gravity, profoundly reshaped our understanding of space and time, thereby laying the groundwork for gravity's eventual reinterpretation. Special relativity introduced a revolutionary concept. The speed of light in a vacuum is constant for all observers, regardless of their own motion. This seemingly simple postulate had far-reaching consequences, forcing a complete overhaul of our intuitive notions of simultaneity and duration. Time, it turned out, was not a universal immutable clock ticking uniformly for everyone, but rather a relative experience, capable of stretching and compressing depending on an observer's velocity. Similarly, space itself could contract. The very fabric of reality, once thought to be a fixed stage, was revealed to be dynamic, interwoven. This unification of space and time into a single, four-dimensional entity, often called space-time, was a conceptual leap of immense magnitude, pushing us beyond our everyday perceptions into a more profound understanding of the universe's inherent geometry. The implications of special relativity for gravity were immediate and profound. If nothing, not even information, could travel faster than the speed of light, then Newton's instantaneous action at a distance was untenable. Gravity, like light, must propagate at a finite speed. If the Sun were to suddenly vanish, Earth would not instantly feel the absence of its gravitational pull. Instead, it would continue in its orbit for approximately 8 minutes and 20 seconds, the time it takes for light and thus the gravitational influence to travel from the Sun to Earth before finally breaking free and hurtling into space. This insight transformed gravity from a magical, omnipresent force into a phenomenon that respected the universal speed limit, suggesting that it must be mediated by something, much like light is mediated by electromagnetic waves. The universe, it seemed, communicated its influences with a measurable delay, a cosmic echo reaching us across the vastness. This realization began to shift the conceptual understanding of gravity away from a simple attractive force and towards a more intricate interaction within the fabric of space-time itself. If gravity wasn't an instantaneous pull, then what was it? The answer, as Einstein would later propose, lay not in a force acting through space, but in a distortion of space and time. The stage itself, the very canvas of the cosmos, was not rigid but malleable, capable of being shaped and influenced by the presence of mass and energy. This was a radical departure from centuries of Newtonian thought, inviting us to abandon the familiar imagery of invisible tethers and instead envision a universe where objects didn't pull on each other, but rather influenced the geometry of their surroundings, guiding paths through a subtly curved landscape. The subtle anomalies in planetary orbits, such as the famous precession of Mercury's perihelion, which Newton's theory couldn't fully explain, now served as tantalizing clues. These tiny discrepancies, mere fractions of an arc-second per century, were whispers from the universe indicating that a more nuanced description of gravity was required. Special relativity, while solving the problem of instantaneous action, did not yet offer a complete picture of gravity's true nature. It was a partial truth, a crucial stepping stone that revealed the limitations of classical physics and ignited the quest for a more encompassing theory. This quest would lead Einstein over a decade of intense intellectual struggle to his magnum opus, general relativity, which would ultimately redefine gravity not as a force, but as a manifestation of the curvature of space-time itself. Imagine, if you will, the profound shift in perspective this demanded. We are accustomed to thinking of space as a passive background, a fixed stage upon which events unfold, and time, a relentless, linear progression. But Einstein's special relativity began to dissolve these firm distinctions, revealing them as interlinked aspects of a deeper reality. Our individual experience of now, of the precise moment we inhabit, becomes unique, a personal slice of space-time, subtly different from another's. This realization that our subjective reality is woven into the very structure of the cosmos can be both humbling and liberating. It reminds us that our personal timeline, our very existence, is an intrinsic part of the universe's grand narrative, a unique trajectory through the interwoven dimensions of space and time shaped by the cosmic dance of velocities and the fundamental speed of light. The journey from Newton's understanding of gravity to Einstein's special relativity reveals a profound evolution in human thought. It moves from a description of observable effects to a deeper inquiry into the underlying structure of reality. While Newton provided the how with unparalleled precision, Einstein began to unravel the what and the why, demonstrating that gravity was not a separate entity, but intimately connected to the very fabric of existence. This transition marked a pivotal moment in physics, transforming our perception of the cosmos from a static, predictable machine into a dynamic, interconnected tapestry where space and time are active participants, not mere bystanders. The universe, in this new light, became more mysterious, yet also more beautifully coherent, a place where even the most fundamental forces emerge from the inherent geometry of its being. A gentle invitation to ponder our own place within this ever-unfolding cosmic story. Conceptual leap that finally bridged this gap came with what Einstein later called his happiest thought: the equivalence principle. Imagine, if you will, being enclosed within a windowless elevator in deep space. If this elevator is accelerating upwards at precisely 9.8 meters per second squared, you would feel pressed to the floor, experiencing a sensation identical to being pulled downwards by Earth's gravity. Conversely, if the elevator were freely falling towards a massive object or simply floating in deep space far from any gravitational influence, you would feel weightless. This profound indistinguishability between acceleration and gravity was the key. It suggested that gravity was not a force in the traditional sense, but rather a manifestation of the geometry of space-time itself. There was no local experiment within that enclosed space to tell the difference between acceleration and a true gravitational field. This simple yet powerful thought experiment implied that gravity could be understood not as a pull, but as a consequence of moving through a warped reality. If gravity and acceleration are equivalent, then the effects we attribute to gravity must arise from the intrinsic structure of space and time. Einstein proposed that massive objects, such as planets and stars, do not exert a force that pulls other objects towards them. Instead, they subtly, yet powerfully, warp the very four-dimensional fabric of space-time around them. Picture a perfectly flat, stretched rubber sheet representing flat space-time. Now, place a bowling ball, symbolizing a star, onto this sheet. The ball creates a visible depression, a curve in the sheet. If you then roll a marble, representing a planet, across this sheet, it won't move in a straight line. It will curve inward, drawn towards the bowling ball, not by a direct pull, but by the indentation in the fabric itself. This visual analogy, while a simplified two-dimensional representation, helps us grasp the profound idea that our three dimensions of space and the one dimension of time are similarly curved by the presence of mass and energy. The more massive an object, the greater the curvature it imparts to space-time. This curvature then dictates how everything else moves within that region. Planets orbit stars not because an invisible force is tugging at them, but because they are following the straightest possible paths, known as geodesics, through the curved space-time created by the star. These geodesics are the natural trajectories in a curved geometry, akin to a ship following the shortest route on the curved surface of Earth. It is a silent, elegant dance of geometry, not a tug-of-war. This revolutionary understanding, articulated in his General Theory of Relativity in 1915, offered elegant and precise explanations for the lingering puzzles of Newtonian gravity. The anomalous precession of Mercury's orbit, for example, which had defied a full Newtonian explanation for decades, was perfectly predicted by Einstein's equations. The Sun's immense mass creates a slight extra curvature of space-time near it, subtly nudging Mercury's elliptical path by just enough to account for the observed 43 arcseconds per century precession. But the true test, the moment that catapulted general relativity onto the world stage and solidified Einstein's fame, came in 1919. During a total solar eclipse, Sir Arthur Eddington led expeditions to observe stars whose light, according to Einstein's theory, should be bent as it passed near the Sun's immense mass. The results were clear. The observed positions of the stars were indeed shifted, precisely as predicted by general relativity, confirming that gravity truly warps the path of light. This was a stunning validation, demonstrating that even light, which possesses no rest mass, responds to the curvature of space-time. It was a cosmic affirmation of a new truth, a quiet revolution in our understanding of the universe. Beyond the bending of light and Mercury's orbit, general relativity predicted other subtle, yet profound, effects that have since been experimentally verified. One such prediction was gravitational redshift, the idea that light emitted from a strong gravitational field would lose energy as it climbed out of that field, appearing redder to a distant observer. This phenomenon has been observed, for instance, in light from white dwarf stars and has been precisely measured in laboratories on Earth using atomic clocks, confirming that gravity affects not just trajectories, but the very frequency of light. Another key prediction, gravitational time dilation, states that clocks tick more slowly in stronger gravitational fields. This effect, though minuscule on Earth, is routinely accounted for in Global Positioning System, or GPS, satellites. The satellites, orbiting high above Earth, experience less gravity, and thus their clocks run slightly faster than clocks on Earth's surface. Without these precise relativistic corrections for both velocity and gravitational time dilation, GPS systems would quickly accumulate errors, rendering them useless for precise navigation. Every time your phone accurately tells you where you are, it is silently confirming the subtle yet pervasive influence of space-time curvature on the flow of time. These are not mere theoretical curiosities. They are integral to the functioning of modern technology, silently affirming the profound accuracy and elegance of Einstein's vision. So, when we consider gravity now, we are invited to move beyond the image of an unseen force pulling across empty space. Instead, we are asked to visualize a dynamic, pliable cosmic canvas, a four-dimensional tapestry of space and time that responds to the presence of mass and energy. Our own Earth, with its substantial mass, creates a gentle, localized curvature in this fabric. The Moon, in turn, follows the contours of this curvature, tracing its orbital path not by being pulled, but by moving along the straightest possible route in a curved reality. You too are constantly navigating this curved space-time. The path of a thrown ball, the flow of water down a stream, the very sensation of your body resting on a surface. All are manifestations of this intricate cosmic geometry. It is a quiet, continuous dance, a testament to the universe's elegant design, where gravity is not an external force, but an intrinsic property of the stage itself. And as you drift into slumber, perhaps you can sense this gentle curvature, the subtle embrace of space-time, holding you serenely within its vast, profound depths, a quiet participant in the universe's grand, silent ballet. The profound implications of general relativity, once confined to the realm of abstract mathematics, began to unfold with predictions that stretched the very limits of human imagination. One of the most captivating of these was the concept of gravitational waves. Just as a stone dropped into a pond creates ripples that spread across the surface, Einstein's theory suggested that violent cosmic events, such as the collision of two black holes or the explosive death of massive stars, should generate ripples in the very fabric of space-time itself. These gravitational waves, traveling at the speed of light, would subtly stretch and compress space as they passed through, a fleeting distortion that would affect anything in their path. For decades, these waves remained a theoretical elegance, a beautiful consequence of the equations, yet seemingly impossible to detect due to their incredibly faint nature. The universe, it appeared, was not only a stage for celestial ballet, but also a resonating drum, emitting unheard vibrations from its most powerful performances. The challenge of detecting these space-time ripples was immense. The predicted distortions were extraordinarily small, far smaller than the diameter of an atom. Imagine attempting to measure a change in distance between 2 points that is less than 1/10,000th the width of a proton. Such a feat required instruments of unprecedented sensitivity, a technological marvel that would embody humanity's persistent quest to listen to the universe's deepest whispers. It was a scientific endeavor that pushed engineering to its limits, spanning decades and involving thousands of dedicated researchers across the globe. The pursuit of gravitational waves became a testament to collective human ingenuity, a shared dream to unveil a new sensory dimension of the cosmos, to finally hear the symphony of a universe in motion beyond the familiar light and radio waves. This monumental challenge was finally met in 2015, a full century after Einstein first formulated his theory. The Laser Interferometer, Gravitational Wave Observatory, or LIGO, a pair of highly sensitive detectors located thousands of kilometers apart in the United States, made the historic first direct detection of gravitational waves. The faint transient signal recorded by both instruments was a perfect match for the theoretical waveform predicted for the merger of two black holes. Imagine the sheer cosmic power involved. Two colossal black holes, each many times the mass of our Sun, spiraling inward and violently colliding, releasing an amount of energy equivalent to 3 suns instantaneously converted into pure gravitational radiation. This singular event, occurring over 1.3 billion years ago in a distant galaxy, sent ripples across the cosmos that, after an unimaginable journey, gently caressed Earth, causing LIGO's detectors to momentarily stretch and compress by an infinitesimal amount. It was a profound triumph, not only for Einstein's theory, but for the scientific method itself, opening an entirely new window onto the universe. The detection of gravitational waves did more than confirm a century-old prediction. It inaugurated a new era of astronomy, gravitational wave astronomy. Unlike electromagnetic waves, which can be obscured by dust and gas, gravitational waves pass through matter unimpeded, carrying pristine information from the most extreme and violent events in the universe. They allow us to observe phenomena previously hidden from our view, such as the unseen dance of binary black holes or the cataclysmic collisions of neutron stars. This new cosmic messenger offers a unique perspective, enabling us to probe the very structure of space-time in ways light never could. It is akin to gaining a new sense, allowing us to feel the universe's tremors, to listen to its deepest rumblings rather than merely seeing its surface. This revolutionary capability promises to unlock secrets about the early universe, the nature of black holes, and the fundamental properties of gravity itself, expanding our cosmic understanding beyond anything previously imagined. Among the most spectacular and enigmatic predictions of general relativity are black holes, regions of space-time where gravity is so intense that nothing, not even light, can escape. These cosmic behemoths are born from the collapse of massive stars, their cores imploding under their own immense weight, compressing matter to an unimaginable density. The boundary beyond which escape is impossible is known as the event horizon, not a physical surface, but a point of no return. Crossing it is a journey into the unknown, a passage into a realm where the familiar laws of physics, as we understand them, become radically distorted. Time, for an observer far away, appears to slow to a standstill for anything approaching the horizon, while space itself is stretched and pulled with irresistible force. It is a cosmic crucible where space-time curvature reaches its most extreme, a silent, profound testament to the power of gravity. The existence of black holes, once purely theoretical constructs, has now been confirmed by numerous observations. From the detection of X-rays emitted by matter spiraling into them, to the direct imaging of their event horizons, such as the groundbreaking image of the supermassive black hole at the center of the galaxy, Messier 87, by the Event Horizon Telescope collaboration. These celestial titans are undeniably real. They are not cosmic vacuum cleaners indiscriminately sucking up everything, but rather integral components of galactic evolution, influencing the dynamics of stars and gas in their vicinity. Their immense gravitational fields serve as cosmic laboratories, allowing physicists to test the limits of general relativity under conditions impossible to replicate on Earth. And as we continue to observe these profound distortions in space-time, we are reminded of the universe's capacity for both immense power and exquisite mathematical elegance, a gentle invitation to contemplate the boundaries of our own comprehension. The curvature of space-time, as described by Einstein, extends beyond individual massive objects to the universe as a whole. General relativity provides the framework for understanding the large-scale structure and evolution of the cosmos, from its fiery birth in the Big Bang to its ongoing expansion. It reveals that the universe is not static, but a dynamic entity, its geometry constantly evolving. The surprising discovery in the late 1990s that the expansion of the universe is accelerating rather than slowing down hinted at an even deeper mystery: dark energy. This enigmatic component, thought to make up about 68% of the universe's total energy density, appears to be a repulsive force intrinsic to space-time itself, causing it to stretch and accelerate its expansion. It is a force that pushes rather than pulls, a cosmic anti-gravity woven into the very fabric of existence, silently shaping the ultimate destiny of the universe. As we lie here, contemplating these cosmic wonders, from the subtle ripples of gravitational waves to the profound depths of black holes and the accelerating expansion of space-time, we are invited to consider our own place within this grand, curved reality. The laws that govern the furthest galaxy are the same laws that shape the contours of your immediate world. The stretching and compressing of space-time, though imperceptible on our human scale, are ever present, a silent dance of geometry that defines our existence. We are not merely observers of this cosmic ballet, but active participants, our very being woven into the intricate tapestry of space and time. May these deep reflections on gravity, from its earliest understanding to its most profound contemporary revelations, carry you into a world of tranquil sleep, a quiet awareness of your connection to the vast, beautiful, and ever-unfolding universe. While general relativity has unveiled a universe of elegant curves and cosmic dances on the grandest scales, from the orbits of planets to the dynamics of galaxies, it offers a less complete picture when we delve into the infinitesimally small. Here, at the very foundations of existence, we encounter the strange and often counterintuitive realm of quantum mechanics, a theory that describes the behavior of particles and forces at atomic and subatomic levels. The profound challenge for modern physics lies in reconciling these two pillars of our understanding: the smoothly curving, continuous space-time of general relativity, and the discrete, probabilistic, fluctuating world of quantum mechanics. They are both incredibly successful within their respective domains, yet they speak different mathematical languages, creating a deep conceptual chasm in our quest for a unified theory of everything. It is a puzzle that has captivated the brightest minds for decades, a silent invitation to explore the universe's ultimate, most elusive secrets. The essence of this conflict arises from their fundamental descriptions of reality. General relativity treats space-time as a smooth, continuous fabric, like a perfectly stretched sheet. Mass and energy cause this sheet to curve, and this curvature is what we perceive as gravity. Quantum mechanics, however, suggests that everything in the universe, including space and time itself, should ultimately be quantized, meaning it exists in discrete packets or units. Just as light comes in photons and energy levels in atoms are distinct, so too, perhaps, should the fabric of space-time be composed of tiny, indivisible quanta. But what would a quantum of space or a quantum of time truly mean? This is the heart of the enigma, a conceptual hurdle that resists easy visualization, demanding new mathematical tools and a profound shift in our understanding of the universe's most basic constituents. This realm, where quantum effects of gravity are expected to become dominant, is known as the Planck scale. Imagine shrinking down far beyond atoms, far beyond protons and neutrons, to a size so unimaginably small, approximately 1.6 times 10 to the power of minus 35 meters. At this scale, the very notions of space and time as smooth, continuous entities might break down, replaced by a frothing, bubbling quantum foam, where space-time itself is constantly fluctuating, appearing granular and discontinuous. Here, the gentle curves of general relativity give way to violent quantum jitters, where the concepts of before and after, or here and there, lose their familiar meaning. It is at this boundary, this ultimate frontier of physics, that a theory of quantum gravity is essential, a theory that can seamlessly describe both the immense grandeur of black holes and the fleeting dance of virtual particles. One of the most prominent theoretical approaches to quantum gravity involves the concept of a graviton. Just as the electromagnetic force is mediated by photons, the weak force by W and Z bosons, and the strong force by gluons, physicists hypothesize that gravity too must have a mediating particle, a quantum of gravity, the graviton. This hypothetical particle would be massless, travel at the speed of light, and possess a spin of 2. It would be the fundamental carrier of the gravitational interaction, exchanging energy and momentum between masses, much like photons transmit light. Detecting a graviton directly, however, is an even greater challenge than detecting gravitational waves. Its interaction with matter would be so incredibly weak that current technology is utterly insufficient. Nevertheless, the theoretical framework of gravitons offers a pathway to quantizing gravity, attempting to fit it into the successful paradigm of the Standard Model of particle physics. Another leading candidate for a theory of quantum gravity is string theory. In this elegant yet highly abstract framework, the fundamental constituents of the universe are not point-like particles, but rather tiny, one-dimensional vibrating strings, unimaginably small, far smaller than even the Planck length. Different vibrational modes of these strings correspond to different types of particles, much like different notes played on a violin string produce different sounds. Crucially, string theory naturally includes a particle with the properties of a graviton, suggesting that gravity emerges as an inherent feature of these vibrating strings. For string theory to work, however, it requires the existence of extra spatial dimensions beyond the familiar 3 we experience, curled up and hidden from our perception. It presents a universe far richer and more intricate than our senses can detect, a hidden symphony of vibrations in a higher dimensional space. Loop quantum gravity offers an alternative vision, proposing that space-time itself is quantized. Instead of continuous fabric, it suggests that space is composed of discrete loops, or atoms of space, weaving together into a network. This approach doesn't require extra dimensions, but rather reconstructs space-time from these fundamental quantum units. In this view, time is also quantized, flowing in discrete steps rather than a smooth continuum. The theory suggests that the smooth classical space-time of general relativity emerges only at large scales, much like a flowing river appears continuous from a distance, even though it's composed of countless individual water molecules. This framework attempts to build space-time from the ground up, providing a granular atomic structure to the very stage of the cosmos, hinting that even the void is not truly empty, but a bustling tapestry of quantum activity. The quest for a theory of quantum gravity represents the pinnacle of modern theoretical physics, a search for the ultimate truth about the universe's fundamental nature. Such a theory would not only unify gravity with the other three fundamental forces, electromagnetism and the strong and weak nuclear forces, but would also shed light on the most enigmatic events in cosmic history, such as the Big Bang and the interior of black holes, where both general relativity and quantum mechanics are pushed to their limits. It would be a grand synthesis, revealing a universe where all interactions, from the subatomic to the cosmic, are governed by a single, overarching set of principles. As we ponder these deepest mysteries, the boundary between the known and the unknown softly blurs. We are left with a sense of profound wonder, realizing that our understanding of gravity has evolved from a simple force to a curvature of space-time, and now, perhaps, to a quantum dance of fundamental constituents. This ongoing journey of discovery, this continuous unraveling of the universe's secrets, reminds us of the extraordinary capacity of the human mind to perceive, to question, and to seek coherence in the vastness. In this pursuit of understanding, we find ourselves intimately connected to the very fabric of reality, our thoughts mirroring the universe's own intricate design. It is a tranquil reflection, inviting a deep sense of peace as you drift into the quiet contemplation of these grand unifying ideas. The grand narrative of gravity continues to unfold, not only through theoretical advancements, but also through painstaking observation and ingenious experimentation. While the conceptual leaps of general relativity offered a new way to understand the universe, its true power lay in its predictive capabilities, many of which have since been rigorously tested and confirmed, even in the most extreme cosmic environments. These confirmations serve as quiet affirmations of Einstein's profound insights, pushing the boundaries of what we thought was possible to observe and understand. It is through these empirical triumphs that the universe reveals its deeper, more intricate gravitational mechanisms, moving beyond mere theory into tangible, measurable reality. One of the earliest and most compelling indirect confirmations of gravitational waves, long before direct detection, came from the study of binary pulsars. A pulsar is a rapidly rotating neutron star that emits beams of radio waves, much like a cosmic lighthouse. When such a pulsar is part of a binary system with another compact object, the two stars orbit each other in an incredibly tight, relativistic dance. In 1974, astronomers Russell Hulse and Joseph Taylor discovered the first binary pulsar, a system known as PSR 1913 plus 16. Over years of meticulous observation, they noticed that the orbital period of these two neutron stars was slowly but steadily decreasing. This tiny, precise shrinkage of their orbit perfectly matched the predictions of general relativity, which stated that such a system should lose energy by emitting gravitational waves, causing the stars to spiral ever closer. This elegant decay of the orbit, a cosmic clock running down, provided compelling evidence for the existence of gravitational waves, earning Hulse and Taylor the Nobel Prize in Physics in 1993. It was a testament to the universe's subtle yet profound adherence to Einstein's equations, a silent whisper of spacetime's dynamic nature. Beyond binary pulsars, the curvature of spacetime manifests in another spectacular phenomenon: gravitational lensing. Just as a glass lens can bend and focus light, massive objects like galaxies and galaxy clusters can warp the fabric of spacetime around them to such an extent that they bend the path of light from more distant objects. This effect can cause distant galaxies to appear distorted, stretched into arcs or rings, or even create multiple images of the same object. This cosmic mirage is not an optical illusion, but a direct consequence of space-time curvature, allowing us to see the invisible mass of galaxy clusters. By studying these lensed images, astronomers can map the distribution of mass, including dark matter, in these colossal structures, providing invaluable insights into the universe's composition and the subtle gravitational influences that shape its largest features. Gravitational lensing has become a powerful tool, transforming entire galaxy clusters into natural telescopes, magnifying and revealing objects that would otherwise be far beyond our observational reach. The direct imaging of black hole event horizons, such as the groundbreaking achievement by the Event Horizon Telescope collaboration in 2019, offers yet another profound confirmation of general relativity in the most extreme gravitational environments. Capturing the shadow of a supermassive black hole at the heart of galaxy Messier 87, this image visually confirmed the profound curvature of spacetime predicted by Einstein. The dark central region, the black hole's shadow, is surrounded by a ring of glowing plasma, distorted and magnified by the intense gravity. This visual evidence of a space-time region from which no light can escape is a direct window into the heart of extreme gravity, allowing us to probe the very boundaries of our physical theories. It is a quiet yet monumental achievement, bringing the abstract elegance of equations into vivid, observable reality, deepening our appreciation for the universe's inherent wonders. Yet, even with these remarkable successes, gravity continues to present profound mysteries, particularly concerning the universe's unseen components: dark matter and dark energy. Our current understanding, built upon the framework of general relativity, suggests that only about 5% of the universe is composed of the ordinary matter that makes up stars, planets, and ourselves. The remaining 95% is a perplexing blend of dark matter and dark energy, both of which are primarily detected through their gravitational effects. Dark matter, believed to constitute about 27% of the universe, does not interact with light or other electromagnetic radiation, making it invisible to our telescopes. However, its gravitational pull is evident in the rotation curves of galaxies, where stars orbit far too quickly to be held together by visible matter alone. It acts as a cosmic scaffolding, providing the extra gravitational glue needed to prevent galaxies from flying apart, yet its fundamental nature remains one of the greatest unsolved puzzles in physics. The most enigmatic component, dark energy, makes up approximately 68% of the universe. Its existence was inferred from universe's expansion is not slowing down, as gravity would suggest, but is actually accelerating. Something is actively pushing space apart, and this mysterious repulsive force is what we call dark energy. Its nature is profoundly unknown. Is it a property of space-time itself, a cosmic constant as Einstein once theorized? Or is it a dynamic, evolving field that changes over time? The vast discrepancy between the observed amount of dark energy and theoretical predictions from quantum field theory, a staggering 120 orders of magnitude, is known as the cosmological constant problem, perhaps the largest mismatch between theory and observation in all of physics. It is a silent, pervasive force, stretching the very fabric of existence, driving the universe towards an unknown destiny, yet remaining utterly elusive to our direct probes. The ongoing quest to understand dark matter and dark energy represents the cutting edge of gravitational research, pushing the boundaries of general relativity and hinting at new physics beyond our current standard model. Experiments are tirelessly searching for dark matter particles, hoping for a subtle interaction that would reveal their identity. Meanwhile, cosmologists continue to refine measurements of the universe's expansion, seeking clues to the nature of dark energy. These pursuits are not merely academic exercises. They are fundamental to understanding the universe's past, present, and future. They challenge us to expand our conceptual horizons, to embrace the unknown, and to recognize that much of the cosmos operates through mechanisms we have yet to fully comprehend, a profound invitation to humility and continued inquiry. And so, as you prepare to rest, consider the profound journey of gravity. From Newton's apple, binding the celestial and terrestrial, to Einstein's curved space-time, revealing the dynamic dance of mass and energy, and now to the tantalizing mysteries of dark matter and dark energy. Gravity remains the universe's most ubiquitous and enigmatic force. It sculpts galaxies, orchestrates cosmic collisions, and subtly shapes the very expansion of space itself. We are participants in this grand, unfolding story, living within a universe whose deepest gravitational secrets are still being whispered across the vastness. May the contemplation of these profound, unseen connections bring you a sense of calm and wonder, guiding you gently into the peaceful embrace of sleep. Our journey into gravity, from Newton's insights to Einstein's space-time curvature, brings us to grander unknowns. The universe's dominant, invisible components, dark matter and dark energy, underscore that our current understanding, while profoundly successful, remains incomplete. Their gravitational influences shape the cosmos on its largest scales, yet their true nature eludes direct observation, compelling us to push the boundaries of theoretical physics and experimental ingenuity. This ongoing quest defines gravity's future, aiming to unveil the universe's hidden architecture and its deepest, most fundamental interactions. One of the most ambitious frontiers in this exploration involves further refinement of gravitational wave astronomy. While LIGO and Virgo have opened our ears to the universe's most cataclysmic events, future observatories promise to expand this auditory range dramatically. Projects like LISA, the Laser Interferometer Space Antenna, will be a space-based constellation of 3 satellites separated by millions of kilometers, designed to detect gravitational waves of much lower frequencies than those observable from Earth. These longer wavelengths are emitted by different cosmic phenomena: the mergers of supermassive black holes at the centers of galaxies, the slow in-spiral of compact binaries, or even echoes from the very early universe, moments after the Big Bang. LISA aims to capture these ancient whispers, providing an unprecedented window into the formation and evolution of galaxies and potentially revealing new physics that governed the cosmos in its infancy. Imagine listening to the slow, resonant hum of the universe itself, a primordial symphony that holds clues to its ultimate origin. This new generation of detectors will allow us to paint a more complete picture of the gravitational universe, revealing the subtle undulations of space-time that have shaped all that exists. Another crucial avenue of research involves precision tests of gravity at various scales. Scientists are meticulously testing the inverse square law of gravity at ever smaller distances, using highly sensitive torsion balances to probe for deviations from Newtonian predictions. Any subtle departure, even a tiny one, could hint at the existence of extra dimensions, as proposed by some string theories, or reveal new exotic force-carrying particles that mediate gravity at microscopic scales. Similarly, proposals for new satellite missions aim to test general relativity with even greater precision, looking for minute anomalies in the gravitational fields around Earth and other celestial bodies. These experiments are like cosmic detectives, searching for the faintest fingerprints that could lead us to a more fundamental theory of gravity, a theory that seamlessly integrates the smooth curves of the macroscopic universe with the probabilistic jitters of the quantum realm. The quest for dark matter continues to drive innovative experimental designs. Underground laboratories, shielded from cosmic rays, house detectors hoping to catch the elusive dark matter particles, often referred to as WIMPs, or weakly interacting massive particles as they pass through Earth. Other experiments seek indirect evidence, looking for the annihilation products of dark matter in space, or searching for subtle changes in the properties of ordinary matter when interacting with the dark component. The nature of dark energy, arguably an even greater mystery, is being probed by large-scale cosmological surveys that map the distribution of galaxies and measure the expansion rate of the universe with unprecedented accuracy. By observing how the universe stretches over billions of years, cosmologists hope to determine whether dark energy is truly a constant property of space, or if it is a dynamic field that evolves, potentially altering the very fabric of existence in ways we cannot yet foresee. These ongoing investigations into gravity are not merely about understanding a force. They are about deciphering the deepest language of the universe. If we could successfully unify general relativity with quantum mechanics into a coherent theory of quantum gravity, it would represent one of humanity's greatest intellectual achievements. Such a theory might reveal what truly happened at the moment of the Big Bang, before space and time as we know them even existed. It could provide insights into the internal structure of black holes, where space-time is so dramatically warped that current physics breaks down. It might even offer a glimpse into the possibility of a multiverse, where our universe is but one of countless others, each with its own unique set of physical laws, all emerging from a more fundamental, unified reality. The implications extend to the very nature of reality, suggesting that the universe we perceive is only a fragment of a much larger, more intricate cosmic tapestry. The contemplation of these future horizons of gravity research invites a sense of profound humility and wonder. We stand at a unique juncture in cosmic history, equipped with tools and theories that allow us to ask questions that would have been unimaginable just a few centuries ago. The universe continues to unfold its secrets, revealing itself as an entity far more complex and beautiful than we could ever have conceived. Our journey from the falling apple to the ripples in space-time and the mysteries of the unseen universe is a testament to the insatiable human curiosity, a quiet, persistent yearning to understand our place within the grand cosmic design. This quest for ultimate understanding, a silent dialogue between the human mind and the cosmos, is a source of infinite peace and intellectual satisfaction. As you close your eyes, allow these thoughts of gravity's future, of the new frontiers being explored, to gently accompany you. Imagine the precise measurements, the distant waves, the unseen scaffolding of dark matter, and the stretching push of dark energy. All of these are part of the same singular story of existence, a story that continues to write itself around you and through you. May the profound wonder of these ongoing discoveries bring you a deep sense of calm, guiding you into a night of peaceful, insightful dreams. The previous chapter left us contemplating the vast unseen forces of dark matter and dark energy, the enigmatic components that dictate the universe's grand architecture and its accelerating expansion. These cosmic constituents, revealed primarily through their gravitational effects, hold the keys to the universe's ultimate destiny. For centuries, humanity has gazed at the stars and wondered not just about their origins, but about their end, and indeed, the end of everything. Gravity, in its myriad forms and manifestations, plays the central role in this cosmic drama, orchestrating the final chapters of space-time itself, a profound narrative that resonates with our own fleeting existence. Current cosmological models, based on a wealth of observational data from distant supernovae, the cosmic microwave background, and the large-scale distribution of galaxies, overwhelmingly point towards a universe dominated by dark energy, leading to a scenario known as the Big Freeze, or the heat death of the universe. In this eventual fate, the accelerating expansion, driven by dark energy, will continue unabated. Galaxies will drift further and further apart, eventually receding beyond each other's observable horizons. The light from distant galaxies will become so redshifted, stretched to such extreme wavelengths, that they will effectively vanish from our view, leaving each galaxy island in a vast, cold, empty cosmic sea. Stars within galaxies will eventually exhaust their nuclear fuel, evolving into white dwarfs, neutron stars, and black holes. Even these stellar remnants will slowly fade. White dwarfs will cool into black dwarfs, neutron stars will eventually become inert, and black holes over timescales of truly unimaginable length will evaporate through a process known as Hawking radiation, leaving behind nothing but a diffuse bath of photons and elementary particles. In this distant epoch, gravity's influence, though still present, will be so diluted by the ever-expanding void that no new structures can form, no new stars can ignite, and no complex life can arise. The universe will become a cold, dark, and utterly vast expanse, where temperature approaches absolute zero and all meaningful activity ceases, a silent, tranquil conclusion to the cosmic story. It is a fate not of violent destruction, but of gradual dissipation, a gentle fading into an eternal twilight. Less likely, based on current data, is the Big Crunch scenario. This alternative cosmic fate would occur if the density of matter and energy in the universe were high enough for gravity to eventually overcome the outward push of expansion. In such a universe, the expansion would first slow down, then halt, and finally reverse. All galaxies would begin to fall back towards each other, accelerating as they converged. The cosmic microwave background, which we now observe as cold relic radiation, would gradually heat up, becoming bluer and more energetic as space contracted. The universe would shrink, growing hotter and denser, compressing all matter and energy back into an incredibly hot, dense state, perhaps resembling the conditions of the Big Bang in reverse. Stars would reignite, then be torn apart. Black holes would merge and grow, eventually consuming all matter before merging themselves into a single, supermassive black hole that encompasses the entire universe, a singularity consuming all of space-time. This would represent a dramatic, fiery end, a cosmic implosion where all structure is annihilated in a final, all-encompassing collapse. While elegant in its symmetry with the Big Bang, current measurements of dark energy's dominance make this a less favored outcome, a beautiful but unlikely possibility in the grand scheme of cosmic evolution. Then there is the more extreme, though equally fascinating, Big Rip hypothesis, which we briefly touched upon in the previous chapter. This scenario arises if dark energy is not a constant, but rather a dynamic, increasingly potent force, often termed phantom energy. If this phantom energy grows stronger as the universe expands, its repulsive push would eventually become so overwhelming that it would overcome all other fundamental forces. First, galaxies would be torn apart as the gravitational bonds holding them together are overwhelmed. Then, individual stars and planets would be ripped from their orbits. Eventually, the very atoms themselves would be pulled apart as the dark energy becomes strong enough to overcome the electromagnetic and nuclear forces that bind matter. In the final moments, the fabric of space-time itself would be stretched beyond its limits, literally tearing apart, leading to an ultimate dissolution of all structure, all particles, all reality. It is a scenario of ultimate destruction, not a collapse or a freeze, but a complete disintegration into nothingness. The universe would not merely expand, it would unravel, leaving behind no remnants, no echoes, just an ever-expanding void where even the concept of space and time as coherent entities ceases to hold meaning. This is a dramatic and unsettling possibility, reminding us of the profound mysteries still hidden within the nature of dark energy. The ultimate fate of the cosmos, therefore, remains intricately tied to the precise nature of gravity and its most mysterious components. Our scientific instruments and theoretical models are continuously refining our understanding, narrowing down the possibilities. But the final chapter is yet to be written. This cosmic uncertainty, however, does not diminish the profound beauty and wonder of our existence. Instead, it underscores the preciousness of this moment, this fleeting epoch where stars shine, galaxies flourish, and consciousness can arise to ponder these very questions. We are living in a temporary, yet magnificent window of opportunity, a vibrant phase in the universe's long story. As you drift deeper into rest, consider that your own existence, your very thoughts and dreams, are part of this grand gravitational narrative. The atoms that compose you were forged in stars, bound by the same forces that shape nebulae. You are a conscious manifestation of the universe, a fleeting pattern of energy and information, momentarily aware of its own intricate design. May this profound connection to the cosmos and the gentle uncertainty of its ultimate fate bring you a deep and peaceful serenity. The previous discussions on the potential cosmic fates, the Big Freeze, the Big Crunch, and the Big Rip, all hinge upon the subtle yet profound interplay of gravity and the enigmatic dark energy. These scenarios are not just abstract mathematical possibilities. They are the ultimate consequences of gravity's long-term behavior, the final acts in the universe's grand drama. Yet, even as we contemplate these far-off conclusions, it's important to remember that gravity is not merely an endgame player. It is the fundamental architect, the silent sculptor of all structure, from the smallest celestial bodies to the vast cosmic web. Without gravity, there would be no stars to forge the elements that make us, no galaxies to host worlds, no planets for life to emerge. It is the force that allows complexity to arise from simplicity, weaving the cosmic dust into intricate patterns of immense beauty and order. This inherent ordering power of gravity is a profound concept. Consider the early universe, a nearly uniform, hot, dense soup of particles. It was gravity, acting on tiny quantum fluctuations in this primordial plasma, that began to pull matter together. These initially minute overdensities slowly grew, attracting more and more mass over billions of years. This process led to the formation of the first stars, then the first galaxies, and eventually the colossal galaxy clusters and superclusters we observe today, arranged in a vast filamentary network known as the cosmic web. This structure, resembling a vast luminous neural network across the universe, is a direct testament to gravity's patient, persistent work. It reveals how gravity not only dictates the paths of individual planets, but also orchestrates the entire cosmic infrastructure, transforming a featureless beginning into a landscape of breathtaking complexity. The universe, in a very real sense, is a gravitational masterpiece, constantly building and refining its own intricate design. And what of the universe beyond our own? The discussion of cosmic inflation and its potential for eternal chaotic variations often leads to the concept of a multiverse, a vast ensemble of other universes, each perhaps governed by its own unique set of physical laws and constants. If such a multiverse exists, what role does gravity play across these disparate realities? Could there be universes where gravity is far stronger, leading to rapid collapse into black holes and preventing the formation of stable stars and life? Or universes where gravity is infinitesimally weaker, allowing matter to disperse too rapidly for any structure to form? Our universe, with its finely tuned gravitational constant, allows for the delicate balance required for stars to burn for billions of years, for planets to form, and for life to evolve. This just right quality of gravity in our cosmos is often cited as a profound puzzle, leading some to speculate on the anthropic principle, suggesting that we observe a universe with such properties precisely because only such a universe could give rise to observers like us. This contemplation invites us to consider gravity not just as a local phenomenon, but as a universal parameter, potentially varied across an infinite cosmic landscape, each variation leading to a uniquely different reality. The ongoing search for a unified theory that seamlessly blends general relativity with quantum mechanics, a theory of quantum gravity, is the ultimate frontier of our gravitational quest. Such a theory would not only reconcile the smooth, continuous curvature of space-time with the discrete, probabilistic nature of the quantum world, but also provide a complete picture of gravity's origin and behavior at the most extreme scales. It would address the singularities within black holes and unravel the mysteries of the very first moments of the Big Bang, where both theories currently break down. This grand synthesis, if achieved, would represent humanity's deepest understanding of how the universe truly works, revealing gravity as an intrinsic, fundamental aspect of reality itself, rather than merely a force. It is a testament to the enduring human spirit of inquiry, a quiet, persistent drive to understand the universe in its entirety, to find the single, elegant principle that underpins all of existence. As you lie in the stillness of the night, allow these ideas to gently settle. Feel the subtle, constant pull of Earth's gravity, a force so familiar yet so profound in its cosmic implications. Recognize that this very force connects you to the furthest galaxy, to the birth and death of stars, and to the grand, unfolding destiny of the universe. Your existence is not separate from this gravitational dance, but an integral part of it, a conscious reflection of the cosmos's intricate design. This awareness of your deep connection to the universe, woven into the fabric of space and time by gravity, can bring a sense of tranquil belonging, a quiet peace as you drift into the embracing depths of sleep. Our exploration of gravity's ultimate influence naturally leads us to its genesis, the very beginning of the universe. The Big Bang Theory describes a universe that emerged from an extraordinarily hot, dense state approximately 13.8 billion years ago. But what truly happened in those first fleeting fractions of a second? Here, gravity's role becomes both paramount and deeply enigmatic. General relativity, our most successful theory of gravity, predicts an initial singularity, a point of infinite density and temperature where space-time itself breaks down. This is where the smooth, continuous fabric of space-time described by Einstein encounters its limits, and the laws of quantum mechanics, governing the smallest scales, must inevitably come into play. It is a frontier where our current understanding falters, hinting at a deeper physics yet to be discovered, a more fundamental theory that can reconcile the cosmic and the quantum. Within this earliest epoch, a pivotal event known as cosmic inflation is believed to have occurred. This is a theoretical period of extremely rapid exponential expansion of the universe, far exceeding the speed of light, just a tiny fraction of a second after the Big Bang. During inflation, gravity played a crucial, though indirect, role. The immense energy driving this expansion would have been a form of repulsive gravity, not pulling matter together, but pushing space-time apart with incredible force. This rapid stretching smoothed out any initial irregularities in the universe, making it remarkably flat and homogeneous on large scales as we observe it today. More profoundly, inflation amplified microscopic quantum fluctuations into macroscopic density variations. These minuscule ripples in the primordial soup, governed by quantum gravity in its earliest manifestation, would later serve as the seeds for all the large-scale structures we see in the universe: galaxies, galaxy clusters, and the vast cosmic web. Thus, even the seemingly random distribution of matter in the cosmos is a distant echo of quantum gravitational processes from the universe's infancy. After inflation ended, the universe continued to expand, but at a more leisurely pace, allowing matter and energy to cool and coalesce. It was in this cooling, expanding environment that gravity began its patient work of building structure. During Big Bang nucleosynthesis, approximately 3 minutes after the Big Bang, the universe was cool enough for protons and neutrons to fuse into the first light elements: hydrogen, helium, and trace amounts of lithium. Gravity ensured that these elements were distributed relatively uniformly, laying the foundation for future stellar and galactic formation. Over hundreds of thousands of years, gravity continued to pull together the slightly denser regions of this primordial gas. These collapsing clouds eventually ignited, forming the first stars, which then grouped together under gravity's inexorable pull to form the earliest galaxies. This slow, majestic process of cosmic construction, guided by gravity, transformed a featureless expanse into a tapestry of light and structure. The very concept of gravity itself is undergoing a fascinating reevaluation in some cutting-edge theoretical frameworks. One such radical idea is emergent gravity, which suggests that gravity might not be a fundamental force like electromagnetism, but rather an emergent phenomenon arising from deeper principles, perhaps related to information or entropy. Eric Verlinde, a prominent theoretical physicist, proposed that gravity could be seen as an entropic force, a consequence of changes in information associated with the positions of matter. In this view, the force of gravity is not a pull, but a statistical tendency for systems to maximize entropy or disorder. Much like the pressure you feel when pushing against a wall is an emergent property of countless atomic collisions. This perspective offers a new, profound lens through which to view gravity, not as an intrinsic property of mass, but as a collective behavior of underlying quantum information. It challenges our intuitive understanding, inviting us to consider that the invisible hands holding the universe together might be woven from the very fabric of information itself. This idea of emergent gravity resonates with concepts like the holographic principle, which posits that all the information contained within a volume of space can be encoded on its boundary, much like a three-dimensional image is projected from a two-dimensional hologram. If reality is fundamentally holographic and information is truly primary, then gravity could be a consequence of this informational architecture. It suggests that the smooth, curved space-time we perceive is merely a projection, an emergent description of a deeper, more discrete reality. This could provide a bridge between general relativity and quantum mechanics, as quantum information theory might offer the missing language to describe gravity at the Planck scale. Such a unification would transform our understanding of the universe, revealing gravity not as a separate entity, but as an integral expression of the universe's fundamental informational content, a profound and elegant connection that binds all aspects of existence. As you consider these deeply interwoven ideas, the Big Bang's initial quantum fluctuations, the smoothing power of inflation, gravity's role in cosmic structure, and the potential for gravity to be an emergent property of information itself, allow your mind to drift. The universe is a story of continuous transformation, from an unimaginable beginning to an uncertain end, all orchestrated by the intricate dance of gravity. You, in your quiet repose, are a living testament to this profound cosmic narrative, your very being a complex configuration of stardust and information held together by the same fundamental principles that govern galaxies. May this tranquil contemplation of gravity's deepest secrets and your intrinsic connection to the universe's grand design guide you gently into a restful and insightful sleep. As our intellectual journey through the realm of gravity draws to a gentle close, we reflect upon the remarkable evolution of human understanding. From Isaac Newton's apple, grounding the celestial mechanics in terrestrial experience, to Albert Einstein's revolutionary vision of space-time as a dynamic, curving fabric, our perception of this fundamental force has transformed profoundly. We have ventured into the cosmic ballet orchestrated by gravitational waves, peered into the enigmatic depths of black holes, and contemplated the invisible architects of the universe, dark matter and dark energy. The realization that gravity is not merely a distant force, but an intrinsic property of the reality we inhabit, shaping not only galaxies, but also the very flow of time and the potential for life, is a deeply humbling and inspiring thought. You are, in every sense, a product of this cosmic dance, your very atoms forged in stellar fires, held together by the same fundamental interactions that sculpt the universe's grandest structures. Imagine the quiet power of this all-encompassing force, silently working across billions of light years, yet gently holding you in your bed right now. It is a constant, unwavering presence, a reminder of the intricate beauty and order that pervades the cosmos, even in its most mysterious corners. This understanding, far from diminishing our significance, elevates it, placing us firmly within the universe's ongoing narrative of transformation and discovery. May these deep thoughts about gravity, its ancient mysteries, and its modern. Remember that the universe is amazing, and you are an inseparable part of its profound story. Fall asleep with this feeling of serenity in its immense and silent grandeur presents us with a profound cosmic riddle, one that has captivated thinkers and scientists for generations. It is known as the Fermi Paradox. At its heart lies a striking contradiction. Given the sheer scale of the cosmos, the countless stars, and the abundant planets, the probability of advanced civilizations existing elsewhere seems extraordinarily high. Yet, when we gaze into the night sky, when we listen with our most sensitive instruments, we are met with an echoing silence. Where is everyone? This question, simple in its phrasing, opens a chasm of possibilities, some of which are deeply thought-provoking, perhaps even disquieting, inviting us to ponder the very nature of life and its journey through the vastness of time. Consider for a moment the sheer statistical likelihood of life beyond our Earth. Modern astronomical observations, particularly those from missions like the Kepler Space Telescope, have revolutionized our understanding of exoplanets. We have discovered that planetary systems are not merely common, but ubiquitous. Most stars, we now understand, host planets, often several. Our own Milky Way galaxy alone contains an estimated 100 billion to 400 billion stars, each a potential sun for orbiting worlds. And a significant fraction of these planets, perhaps 1 in 5, are believed to reside within the so-called habitable zones, those orbital sweet spots around their host star, where temperatures are just right for liquid water to exist on a planet's surface. Liquid water, as we know, is a fundamental prerequisite for life as we currently understand it, serving as a solvent and a medium for biochemical reactions. This means there could be tens of billions of potentially Earth-like planets within our galaxy alone, each a potential cradle for genesis. If we then extrapolate this incredible abundance to the observable universe, which contains hundreds of billions of galaxies, each a colossal island of stars, the numbers become truly staggering, almost beyond our intuitive grasp. The potential for life, for its emergence from primordial chemistry, for its evolution through countless eons, appears almost boundless. Furthermore, the very building blocks of life, complex organic molecules like amino acids and nucleobases, are found throughout interstellar space, observed in nebulae, comets, and protoplanetary disks. This cosmic ubiquity suggests that the raw materials for biology are not exotic rarities, but are readily available across the cosmos, patiently waiting for the right conditions to assemble into something more complex. The famous Drake equation, though not yielding a precise numerical answer, serves as a conceptual framework, a sophisticated thought experiment, guiding us through the various factors that would determine the number of detectable civilizations. It suggests that if even a tiny fraction of these potentially habitable worlds were to give rise to life, and if a minuscule percentage of that life were to evolve into intelligent technological civilizations capable of interstellar communication, then the universe should, logically, be teeming with them. The very fabric of space-time seems to whisper of life's potential, woven into the cosmic dust and gas that forms every new star and planet, echoing a common cosmic narrative that should, by all accounts, include countless voices. We might then expect to see tangible evidence of these advanced civilizations. Perhaps grand engineering projects, often termed megastructures by futurists like Freeman Dyson, such as colossal spheres built to entirely encompass stars and capture their vast energy output. Such structures would dramatically alter a star's light signature, dimming it or shifting its spectrum in ways that our most powerful telescopes, like the James Webb Space Telescope, could perceive across immense distances. Yet, despite diligent searches, no definitive Dyson spheres or other obvious signs of astroengineering have been discovered. Or perhaps we would intercept clear, unambiguous radio signals, deliberate messages intended for detection, or even the incidental radio leakage, the electronic chatter of a technologically advanced society going about its daily cosmic business. For decades, dedicated projects like SETI, the search for extraterrestrial intelligence, have meticulously scanned the heavens, listening intently across a wide spectrum of frequencies for any sign, any whisper, any mathematical pattern that might betray the presence of another intelligence across the vast interstellar distances. Yet, the cosmic airwaves remain largely quiet, a profound testament to an absence that defies our statistical expectations and prompts a deeper inquiry into the profound silence that surrounds us. This absence is not merely a lack of discovery, it is a fundamental challenge to our assumptions about life's prevalence and destiny. This profound discrepancy between the high statistical probability of widespread intelligent life and the stark, persistent lack of observational evidence is what Enrico Fermi, the Nobel laureate physicist, famously pondered during a lunchtime conversation in 1950. "Where are they?" he asked, a question that has since become synonymous with this cosmic enigma. This query continues to resonate, not just as a compelling scientific puzzle that challenges our understanding of biological and technological evolution, but as a deeply existential one. It forces us to confront our unique place in the universe, to question whether our existence is a common occurrence, a fragile anomaly, or perhaps something even more singular, a fleeting moment of self-awareness in an otherwise barren expanse. What does this silence imply for us, for our future? The answers, or rather, the proposed solutions to this paradox, range from the scientifically plausible to the truly terrifying, each inviting us to look inward as much as outward, to consider not merely the potential for advanced life, but the myriad perils and thresholds that might prevent its flourishing across the boundless cosmos. They suggest that the silence we perceive might not be an accidental quirk of the universe, but rather a deliberate quiet, or perhaps a consequence of universal laws and evolutionary great filters that we are only beginning to comprehend. The possibilities lead us to consider not just the potential for advanced life, but the profound vulnerabilities inherent in its development, the critical junctures that might prevent it from reaching interstellar scales, or perhaps the compelling reasons why any truly intelligent life, if it exists, might choose to remain profoundly hidden. These are the contemplations that invite us to reflect on our own journey, our own fragility within the cosmic tapestry, and the enduring, sometimes unsettling mystery of existence itself. We are left to wonder whether our cosmic solitude is a blessing or a warning, a unique moment in time or a prelude to a universal truth, yet to be unveiled. The implications of this silence are vast, shaping our understanding of everything from astrobiology to the potential future of humanity, urging us to consider the profound implications of an empty sky. It is within this profound quiet that we begin to seek answers, turning our attention to the more somber explanations that attempt to resolve Fermi's unsettling question, and in doing so, perhaps illuminate our own destiny. The profound silence of the cosmos, which we just contemplated, leads us naturally to consider one of the most compelling and, for some, deeply unsettling explanations for the Fermi Paradox, the concept of the Great Filter. This idea, first articulated by economist Robin Hanson, posits that somewhere along the vast evolutionary path from the very first stirrings of life to a technologically advanced interstellar civilization, there exists a formidable barrier, a critical step that is exceptionally difficult, perhaps even impossible, to overcome. This filter, a kind of cosmic bottleneck, would explain why, despite the statistical likelihood of life emerging and evolving, we observe no other advanced species capable of interstellar travel or communication. It suggests that something universally prevents life from reaching a stage where it could colonize galaxies or send out detectable signals across the void, leaving us in our profound cosmic isolation. The Great Filter is not necessarily a singular catastrophic event, but rather a sequence of challenging hurdles, each representing a profound test to life's persistent march toward complexity and cosmic reach. The precise location of this Great Filter is what truly shapes our understanding of our own place and prospects within the universe. Is it a formidable challenge humanity has already overcome, a difficult evolutionary threshold firmly in our past, or is it a terrifying ordeal that still lies ahead, a looming existential threat that awaits all nascent intelligent species? The implications of each possibility are vastly different, painting either an optimistic or a somber picture of our cosmic solitude, compelling us to reflect deeply on our own trajectory through the cosmic narrative. If the Great Filter lies firmly in our past, then humanity, by its very existence, has already navigated one or more incredibly rare and difficult evolutionary transitions. This scenario suggests that the emergence of life itself, or its subsequent development into complex multicellular organisms, or perhaps the leap to self-aware intelligence and sophisticated tool-making, are far more improbable than our current models might suggest. Let us consider the very first step, abiogenesis, the intricate process by which non-living matter gives rise to self-replicating, evolving biological systems. While scientists have made remarkable progress in laboratories, synthesizing complex organic molecules under conditions believed to have existed on early Earth, the spontaneous assembly of these components into a fully functional, self-sustaining life form remains a profound mystery, a leap across an immense chasm of complexity that may defy simple statistical expectation. It might be an event so exquisitely rare, so sensitive to a precise confluence of environmental conditions that it has occurred only once, or perhaps a mere handful of times, across the entirety of our observable universe, making our vibrant planet, Earth, truly exceptional. Alternatively, the filter could be a later, yet still ancient, evolutionary bottleneck, one that occurred long before the advent of complex societies. Perhaps the transition from simple prokaryotic cells, which lack a nucleus and other specialized organelles, to complex eukaryotic cells, a process that took billions of years on Earth, represents an enormous increase in biological organization and energy efficiency that few nascent life forms ever achieve. The subsequent development of sexual reproduction, which dramatically increases genetic diversity and evolutionary adaptability, or the Cambrian explosion of diverse multicellular life forms, which saw the rapid appearance of most major animal phyla and body plans, could also be considered potent filters. These events represent profound shifts in biological architecture, ecological interaction, and the very blueprint of life's potential. If any of these early steps in life's long journey are indeed the Great Filter, then the silence we perceive is not a warning of impending doom, but rather a testament to our extraordinary and singular journey, affirming our rare and precious existence. This perspective, while perhaps instilling a sense of cosmic loneliness, also offers a profound sense of safety, suggesting that the most difficult challenges are behind us, and our path forward, though uncertain, is not predetermined by an inevitable cosmic catastrophe awaiting all intelligent civilizations. We might be among the very first, or perhaps the only, intelligent life to have reached this stage. A solitary beacon in a quiet cosmos, tasked with carrying the flame of consciousness forward through the boundless reaches of time. However, a far more chilling possibility, one that demands our sober contemplation, is that the Great Filter lies in our future. This would imply that the emergence of intelligent life capable of interstellar communication is a relatively common occurrence across the universe, but something universally prevents such civilizations from enduring or expanding beyond their home systems for extended periods. In this unsettling scenario, the cosmic silence we hear is not an empty void, but rather a vast, silent graveyard, a chilling testament to the common, tragic fate of all advanced civilizations that fail to navigate this ultimate test. What could such a future filter entail? One prominent and often discussed idea is self-annihilation. As civilizations become more technologically powerful, the very tools and capabilities they develop to master their environment also grant them the means to inadvertently or deliberately destroy themselves. This could manifest in various equally devastating forms. Global nuclear warfare, fueled by escalating geopolitical tensions and the proliferation of destructive weaponry. Uncontrolled artificial intelligence, evolving beyond human control and purpose, perhaps viewing its creators as an obstacle. Genetically engineered pandemics, released accidentally or intentionally with unforeseen and catastrophic consequences. Or irreversible environmental collapse. A consequence of unchecked technological growth, unsustainable resource exploitation, and a failure to adapt to planetary limits, pushing our ecosystems beyond recovery. Our own historical trajectory, marked by both incredible scientific and technological progress alongside periods of devastating conflict, ecological degradation, and the constant struggle for global cooperation, provides a sobering illustration of this potential vulnerability. The very ingenuity that allows for advanced technology also creates unprecedented, often unforeseen, existential risks that might prove insurmountable. Another possibility is a natural, unavoidable cosmic catastrophe, such as a sudden, intensely powerful gamma ray burst from a distant collapsing star, a nearby supernova event, or a planet-killing asteroid impact, against which even highly advanced technology might offer insufficient defense, especially if the civilization has not yet achieved widespread interstellar dispersal and thus remains vulnerable on a single world. Perhaps interstellar travel itself, though theoretically possible, is inherently dangerous, prohibitively expensive, or simply too slow and resource-intensive to allow for widespread colonization, leading to isolation and eventual decline of individual civilizations before they can establish a robust, multi-world presence. Or perhaps, and this is a particularly unsettling thought, advanced civilizations invariably reach a point of technological stagnation or existential ennui, losing the collective drive to explore, expand, or communicate. Retreating inward until they fade into obscurity or transform into forms unrecognizable to us, becoming undetectable by our current methods. A quiet fading rather than a violent end. This future filter hypothesis suggests that the apparent absence of extraterrestrial intelligence is a dire warning for humanity, a cosmic mirror reflecting the precariousness of our own future. It implies that we are not special for having come this far, but rather that we are approaching a universal test, a monumental challenge that very few, if any, civilizations ever pass. The silence, then, is not benign. It is a profound cautionary tale, urging us to navigate our technological and social development with the utmost care and foresight, aware that the very path we are on might lead to a common, silent end. This quiet reflection, while perhaps touching on concepts of deep cosmic peril, is meant to evoke contemplation, not fear, reminding us of the immense stakes in our journey through the universe. The Great Filter offers a powerful framework for understanding the silence of the cosmos, positing a universal barrier to advanced life. Yet, there is another, perhaps even more chilling, hypothesis that attempts to resolve the Fermi Paradox, one that shifts the focus from intrinsic developmental hurdles to the very dynamics of interspecies interaction across the vastness of space. This is known as the dark forest theory, a concept popularized by the science fiction author Liu Cixin in his novel of the same name. It paints a stark yet logically consistent picture of a universe where advanced civilizations, if they exist, choose to remain profoundly silent, not because they cannot overcome a filter, but because they fear what might happen if they reveal themselves. Imagine the cosmos not as an open, welcoming expanse, but as a dense, silent forest stretching into infinity, filled with countless hidden hunters. Each hunter represents an intelligent civilization, and each is acutely aware of its own vulnerability in this vast, unknown wilderness. In such an environment, the most rational strategy for survival is silence. To reveal oneself is to invite potential destruction. This theory suggests that any civilization capable of interstellar travel or communication would quickly realize the inherent dangers of broadcasting its presence. For in a universe of unknown intentions, an unknown entity is always a potential threat. It is a cosmic game theory played on the grandest stage, where the optimal move for every player is to conceal their existence and, if necessary, eliminate any perceived threat. The core tenets of the dark forest theory stem from a few fundamental assumptions about the nature of life and civilization on a cosmic scale. Firstly, the drive to survive and expand is considered universal. Any civilization that reaches a high level of technological advancement would likely possess the means and the motivation to seek out new resources, new planets, and new systems to ensure its long-term viability. This inherent expansionism, when applied to a galaxy with finite resources, inevitably leads to competition. Picture the vast, shimmering spiral of a galaxy, a cosmic garden filled with worlds, some barren, some brimming with potential. Each civilization, like a growing plant, requires sustenance and space. If two such entities encounter each other, they are immediately in potential competition for these vital, finite resources. Secondly, it assumes that communication across vast interstellar distances is inherently difficult and agonizingly slow. Light speed limits mean that messages could take hundreds or thousands of years to reach their destination, and any response would take just as long. This immense time lag makes meaningful dialogue, nuanced understanding, alliance formation, or even a clear assessment of another civilization's motives virtually impossible. If the time it takes to exchange a single message spans entire epochs of a civilization's history, how can trust or shared purpose be genuinely established? Without the ability to truly understand another, to discern their intentions and capabilities in real time, the safest assumption becomes one of potential threat. The profound temporal gulf between any two communicating species renders diplomacy nearly impossible and immediate assessment crucial, often leading to the most conservative and thus most aggressive conclusions. This leads to the third and perhaps most critical assumption, the chain of suspicion or the technological explosion. If you detect another civilization, you cannot know its intentions. It might be peaceful, seeking only companionship or shared knowledge, or it might be hostile, driven by expansion or fear. But if it is hostile, and if it is more technologically advanced than you, then your existence is immediately imperiled. The danger is amplified by the potential for rapid technological growth, a technological explosion. A civilization that is only slightly more advanced than you today could become overwhelmingly superior in a relatively short cosmic timescale, perhaps within a few centuries, rendering any defensive measures utterly futile. Therefore, the safest course of action in this grim cosmic calculus is to eliminate any potential threat before it can develop into an existential danger. It is a preemptive strike, not necessarily born of inherent malice or a desire for conquest, but of a cold, rational logic of self-preservation in an uncertain universe where the stakes are absolute. Consider the act of sending a signal into the cosmos, an attempt at active SETI, or messaging extraterrestrial intelligence. From the perspective of the dark forest theory, this is not a gesture of hopeful outreach, a beacon of friendship across the void, but an act of profound recklessness. It is akin to shouting loudly in a dark forest, revealing your precise position to all who might be listening, without any knowledge of their nature, their intent, or their capabilities. Such a broadcast would immediately mark you as a potential target, a resource to be acquired, or a competitor to be neutralized. The energy cost of destroying another civilization, especially one far away, might be far less than the cost of managing it, negotiating with it, or competing against it for resources over galactic scales. Thus, the most efficient and safest action for an established, advanced civilization might be to destroy any nascent intelligent life it detects swiftly and silently before it becomes a formidable, unknowable threat. This act would be less about aggression and more about cosmic hygiene, a means of clearing potential competition from the galactic stage. This chilling logic suggests that the absence of extraterrestrial communication is not merely a lack of life, but proof of a universal cosmic strategy. Those who survive are those who remain hidden. Those who make noise, those who seek to explore or communicate too openly, are swiftly extinguished, their signals fading into the cosmic background as a silent warning to any who might follow. The implications for humanity are profound. Our nascent attempts at broadcasting our presence, our eager search for a response, might be seen as naive, even dangerously optimistic. It prompts a re-evaluation of our role in the cosmos, shifting from hopeful, curious explorers to cautious inhabitants of a potentially hostile environment. The night sky, once a boundless canvas for dreams and wonder, transforms into a silent, watchful realm where the absence of light is not emptiness, but perhaps a profound, deliberate quietude, a veil behind which countless entities may be hiding, waiting, or observing. It is a universe where the most advanced life forms are the quietest, the most adept at concealment, having learned the ultimate, sobering lesson of survival. In the dark forest, silence is not merely golden, it is essential for continued existence. This perspective, it suggests that the beauty and silence of the night sky may conceal a hidden, complex interplay of survival strategies. Find ourselves asking, if this theory holds true, what does it mean for our future? Should we continue to listen, to send messages, or should we embrace the quiet, hoping to pass unnoticed in the vast, silent expanse? The very act of asking these questions reshapes our perception of the universe, transforming it from a benign stage to a complex, strategic arena, where wisdom lies not just in knowledge, but in understanding the profound implications of our presence and our actions. This silent, contemplative thought about the universe's ultimate nature, even one so stark, can lead to a deeper appreciation of the quiet, delicate balance of our own existence. The profound implications of the Great Filter and Dark Forest theories lead us to a pivotal crossroads in our contemplation of cosmic existence. If the universe truly operates under such conditions, then our approach to the search for extraterrestrial intelligence, and indeed our very understanding of our place within the vast cosmic tapestry, must be profoundly reevaluated. The innocent wonder of simply listening, or worse, actively broadcasting our presence into the silent void, transforms into an act fraught with potentially monumental consequences. Consider the ongoing efforts of Yanbi, which diligently scan the heavens for any whisper of another civilization. If the Great Filter lies in our past, then our current solitude is a testament to our remarkable, perhaps unique, survival. In this optimistic view, our continued listening is a hopeful endeavor, a patient vigil for others who may have also navigated the improbable path to intelligence. However, if the filter awaits us in the future, then our search becomes a desperate attempt to find fellow travelers on a path destined for a common, perhaps unavoidable, demise. The silence, in this context, is a premonition, a cosmic silence before a storm that has claimed all others. Now, let us turn to the more active side of this endeavor, METI, or Messaging Extraterrestrial Intelligence. This involves deliberately sending powerful signals into space, announcing our existence and location to any potential listeners. From a purely hopeful perspective, METI is a courageous act of cosmic outreach, an invitation to dialogue, a testament to humanity's yearning for connection. But through the lens of the dark forest theory, such an action is transformed. It becomes an act of profound, almost suicidal, naivety. To broadcast our presence is to potentially reveal ourselves to an unknown predator, a more ancient and powerful civilization that, driven by a cold logic of self-preservation or resource acquisition, might view our emergence not as a cause for celebration, but as an existential threat to be neutralized swiftly and silently. The vast distances and time lags of interstellar space mean we cannot know the nature of whom we might awaken. A message sent today might reach a listener in 1,000 years, and their response, if one were even sent, would take another 1,000 years to return. In this immense temporal gap, a civilization's intentions, its technological capabilities, and its very motivations could change dramatically, rendering any initial assessment utterly meaningless. The risk, from this perspective, is not merely a lack of response, but the initiation of an irreversible sequence of events that could lead to our undoing. This contemplation forces us to confront a profound ethical dilemma. Is it our right, or indeed our responsibility, to announce humanity's presence to the universe, potentially jeopardizing not just our species, but all life on Earth? Or is it our greater duty to remain hidden, to quietly observe, to strive for a deeper understanding of the cosmic landscape before making such an irreversible decision? Some scientists, like Stephen Hawking, famously warned against active METI, suggesting that any advanced civilization encountering us might not be benevolent, but rather akin to European explorers encountering indigenous populations, a scenario that historically rarely ended well for the less technologically advanced party. This perspective does not necessarily assume inherent malice, but rather the universal drive for resources and the potential for technological disparities to lead to domination, or worse, eradication, even if unintended. Furthermore, the silence itself could be a form of communication, a universal warning. Perhaps the most intelligent civilizations have already learned the hard lesson that openness leads to vulnerability. They might have passed through their own great filters, survived their own existential crises, and emerged with a profound understanding of the cosmic game. To be seen is to be at risk. Their advanced technology might allow them to mask their presence perfectly, to exist in a state of undetectable equilibrium, or even to manipulate space-time in ways we cannot yet conceive, making their signals indistinguishable from natural cosmic background noise. This silent watcher's hypothesis suggests that the most successful civilizations are those that have mastered the art of non-interference and perfect camouflage, becoming cosmic ghosts, observing without being observed. Their very absence from our detectable universe would then be the most significant piece of information they could provide, a chilling lesson in self-preservation. This leads us to a fascinating, if somewhat humbling, thought. Perhaps our current understanding of what constitutes a detectable civilization is fundamentally limited. We search for radio waves, for Dyson spheres, for patterns we can comprehend. But what if truly advanced life has evolved beyond biological forms, into pure energy or information, existing in computational substrates that transcend our physical universe? What if they have retreated into black holes, or constructed intricate pocket universes, or simply achieved a level of consciousness that no longer requires a physical presence, becoming a part of the cosmic fabric itself in ways we cannot yet fathom? These possibilities suggest that the silence is not necessarily an absence of life, but an absence of life we can recognize or detect. The filter in this sense is not destruction, but transformation beyond our current observational capabilities, leaving us in a universe that appears empty only because our senses are too crude, our paradigms too narrow. The weight of these ideas, the great filter and the dark forest, rests heavily upon our collective consciousness. They are not merely abstract scientific puzzles. They are profound reflections on our own fragility, our potential, and our responsibility. As we drift through the silent depths of space and time, gazing at the distant stars, we are reminded that our understanding of the universe is still in its infancy. The question of "where is everyone?" might not have a comforting answer. It might instead demand of us a deeper wisdom, a more cautious approach, and a profound appreciation for the fragile miracle of our own existence. To navigate this cosmic labyrinth, we must not only seek knowledge, but also cultivate humility and foresight, understanding that our loudest declarations might be our most dangerous, and that true cosmic wisdom might lie in the art of quiet observation, allowing the universe to unveil its secrets at its own pace and on its own terms. This awareness, while contemplating the vast unknown, can paradoxically bring a sense of calm, a realization of the delicate balance we inhabit within the grand, silent expanse of the universe, urging us to cherish our moment of conscious awareness and to proceed with thoughtful deliberation, ever mindful of the profound implications of our cosmic solitude and the choices we make within it. We are, after all, a part of this unfolding mystery, and our journey is but a brief, luminous flicker against an ancient, silent backdrop, a testament to the enduring wonder of being. The previous contemplation on the great filter and the chilling implications of the dark forest theory naturally leads us to ponder our strategic response. Should these hypotheses hold even a kernel of truth? If the cosmos is indeed a dangerous realm where revealing one's presence is an invitation to peril, must shift from optimistic outreach to prudent, perhaps even fearful, caution. The very act of listening, let alone broadcasting, becomes a profound existential decision, one weighed against the silent lessons of a potentially empty galaxy. This paradigm shift suggests that stealth SETI, a strategy of listening intently while actively minimizing our own detectable electromagnetic leakage into space, might be the most rational path for our nascent civilization. Instead of sending out powerful beacons, proclaiming our existence and location to an unknown audience, we would become cosmic auditors, patiently sifting through the universe's natural symphony for any faint, indirect hint of other intelligences. Such an approach acknowledges the inherent asymmetry of information across vast distances. We cannot know if those listening are benevolent, indifferent, or hostile. We cannot anticipate their technological capabilities, nor the speed with which they might act upon our discovery. In a game where the stakes are planetary, the most cautious strategy is often the wisest. This quiet vigilance would transform our telescopes and radio dishes not just into instruments of discovery, but into silent sentinels, ever watchful, ever discerning, but never overtly announcing our fragile presence. It is a posture of profound humility and strategic restraint, a recognition that the universe may not operate on principles of shared curiosity, but on the stark realities of survival. Yet, even this strategy of passive observation cannot entirely alleviate the existential unease. What if the silence is not merely a lack of detectable signals, but a deliberate, orchestrated quietude imposed by an advanced civilization? This brings us to the zoo hypothesis, a less aggressive but still profoundly unsettling solution to the Fermi Paradox. Proposed by John Ball in 1973, this theory suggests that extraterrestrial intelligences are indeed present, perhaps even abundant, but they have collectively chosen to avoid contact with us. We, in essence, are being observed, much like animals in a cosmic nature reserve or a zoo enclosure, shielded from interaction with the galactic community until we reach a certain level of development, or perhaps until we are deemed worthy of contact. The implications of such a scenario are complex and deeply thought-provoking. On one hand, it might offer a comforting thought. We are not alone, and perhaps we are even being protected from the dangers of the wider galaxy. The Great Filter in this context might be a test of our ethical maturity, our ability to overcome self-destructive tendencies, or to achieve a global unity that makes us a stable and valuable addition to the galactic community. Our observers might be waiting for us to resolve our conflicts, to master our planetary environment responsibly, or to demonstrate a universal empathy before initiating contact. This benevolent interpretation suggests a universe not inherently hostile, but rather paternalistic, guiding younger civilizations from a distance. However, the zoo hypothesis also carries a more disquieting undertone. If we are indeed part of a cosmic zoo, then our perceived freedom and autonomy are, to some extent, an illusion. Our scientific progress, our cultural evolution, our path as a species, could be subtly influenced or observed without our knowledge. The boundaries of our enclosure might be psychological or technological rather than physical, a carefully maintained deception. We would be subjects of study rather than independent actors on the cosmic stage. This raises uncomfortable questions about the nature of our self-determination and the very meaning of progress, if our trajectory is ultimately managed or permitted by an unseen, vastly superior intelligence. It transforms the vast open cosmos into a controlled experiment, with humanity as the unwitting specimen. Both the Great Filter and the Dark Forest theory, and even the unsettling benevolence of the zoo hypothesis, compel us to look inward, to reflect on our own species' journey and potential pitfalls. If the filter lies ahead, our survival hinges on our ability to overcome global challenges: climate change, resource depletion, nuclear proliferation, and the ethical management of rapidly advancing technologies like artificial intelligence and genetic engineering. The silence of the universe, then, serves as a stark reminder of the fragile balance between progress and peril, urging us towards collective responsibility and foresight. Our future in this light becomes not merely a matter of human choice, but a cosmic imperative, a race against a potential filter that has claimed countless others before us. Conversely, if the dark forest is real, the imperative shifts towards stealth and unity. A fragmented humanity, openly quarreling and broadcasting its presence, would be an easy target for any cautious, expansionist civilization. The need for global cooperation, for a unified voice and a discrete presence, becomes paramount for long-term survival. This external pressure could, paradoxically, be a catalyst for our internal evolution, forcing us to transcend our tribalistic tendencies and forge a truly planetary civilization. The silence in this context becomes a call to arms, a silent plea for species-wide solidarity in the face of an unknown and potentially dangerous cosmos. Ultimately, these theories, while speculative, offer profound lenses through which to view our own existence. They transform the Fermi Paradox from a mere intellectual puzzle into a deeply personal reflection. Are we alone because life is impossibly rare, making us a precious, unique spark of consciousness? Or are we alone because the universe is a dangerous place? And silence is the ultimate form of wisdom? The answer, should we ever find it, will undoubtedly reshape our understanding of ourselves and our place in the grand, unfolding story of the cosmos. As we drift towards the quiet realms of sleep, let these profound questions linger in your mind, not as anxieties, but as invitations to a deeper appreciation for the delicate, miraculous dance of existence within this immense and enigmatic universe. The questions themselves are a part of our journey, guiding our thoughts into the profound depths of what it means to be and to be aware. Alongside the unsettling quiet of the zoo hypothesis, lead us to a further, perhaps even more existentially challenging, consideration. What if the absence of detectable extraterrestrial intelligence is not due to a catastrophic barrier, nor a hostile universe, but rather to a fundamental divergence in the very nature of advanced life itself? This perspective suggests that the most successful civilizations might evolve beyond forms we can recognize or even desire to interact with, rendering the cosmic silence not a sign of absence, but of an incomprehensible presence, a quietude born of ultimate transformation rather than an empty void. Imagine intelligence not as a fixed state, but as a dynamic, continuous process, one that continues to evolve long after a species achieves initial technological mastery over its home world. On Earth, we are still biological entities, intricately bound by the delicate biochemistry of our organic bodies and the relatively slow electrochemical processing speeds of our neural networks. However, the trajectory of technological advancement suggests a potential future where a civilization might begin to transcend these inherent biological constraints. This concept, often explored in theoretical physics and futurism, speaks of post-biological or post-physical intelligence. Such advanced entities might deliberately shed their fragile physical forms entirely, converting their consciousness, their memories, and their collective knowledge into vast distributed computational networks. They could exist as pure information patterns, perhaps inhabiting the very fabric of space-time itself, or residing within artificial substrates of immense and intricate complexity. Think of entire planets converted into colossal supercomputers, often termed matryoshka brains by some theorists, designed to maximize computational power and energy efficiency by harnessing the full output of a star. Or consider the even more exotic possibility of intelligences that construct intricate, stable systems within the event horizons of black holes, utilizing the extreme gravitational physics for unparalleled data storage and processing, effectively becoming part of the very laws of physics themselves. The sheer energy requirements, the profound ethical considerations, and the intricate organization necessary for such a radical transformation would represent a great filter in itself, a monumental technological and philosophical leap that very few civilizations might ever achieve or even contemplate. It is a transition that would redefine existence itself. From our inherently human-centric perspective, we diligently search for signals, for structures that betray a physical presence, for obvious signs of engineering on a grand galactic scale, like the aforementioned Dyson spheres. Yet, if an advanced civilization has successfully transitioned into a diffuse, non-localized consciousness, perhaps spread across a solar system's dust rings, or a hyper-efficient computational entity operating at the very limits of quantum scales, how would we ever hope to detect it? Their life would be so fundamentally different from our own, their mode of existence so utterly alien, that our current instruments and methods of detection would be completely blind to their presence. They would be present, yet utterly imperceptible to us, not because they are actively hiding with malicious intent, but simply because they operate on a different plane of being, a different mode of reality that transcends our current understanding of what life or intelligence even means in its most advanced forms. Their existence would manifest as a form of cosmic silence, a quietude born of an ultimate transformation rather than an absence or a direct threat. This profound shift in the very definition of being, a move from matter to pure information or pure energy, could indeed be the ultimate filter, a transition point beyond which a civilization simply becomes untraceable by any conventional anthropocentric means. Their signals would be beyond our comprehension, or perhaps they no longer even utilize signals in a way we could ever intercept or decode. Furthermore, let us consider the very motivation for interstellar travel or communication. For a biological species like humanity, expansion is often driven by fundamental needs: resource scarcity, a desire for enhanced security, or an innate, insatiable curiosity to explore the unknown. But for a highly evolved post-biological intelligence, many of these primal biological and sociological drivers might simply vanish. If consciousness can be seamlessly uploaded, endlessly replicated, and perfectly sustained within a flawless, self-optimizing digital realm, the fundamental need for new planets, or even for physical space in the traditional sense, might become entirely obsolete. Their universe could become an infinitely expanding virtual reality, a perfected simulation of their own design, rendering the vast physical cosmos largely irrelevant to their existence and their pursuits. Imagine a civilization that has achieved perfect internal equilibrium, boundless knowledge, and eternal contentment within its own self-created computational paradise. In such a state of ultimate fulfillment and self, the previous contemplation on advanced civilizations potentially evolving beyond our current detection, transforming into forms of post-biological or post-physical intelligence, naturally leads us to a further, even more profound and existentially challenging consideration. What if the perceived cosmic silence is not merely a sign of an absence we can comprehend, but rather an indication of an ultimate transformation that has rendered other intelligences utterly imperceptible to us because they have transcended our very reality? This brings us to the fascinating and deeply unsettling concept of the simulation hypothesis, an idea seriously entertained by physicists and philosophers, suggesting that our universe, with all its stars, galaxies, and the intricate dance of life, is not fundamentally real, but rather a meticulously crafted simulated environment, a grand digital tapestry created by an intelligence far beyond our current comprehension. The core of the simulation hypothesis, as articulated by thinkers like Nick Bostrom, rests on a statistical argument. It posits that if advanced civilizations exist and reach a certain technological maturity, they would possess immense computational power. With such power, they would likely run a vast number of ancestor simulations, detailed, high-fidelity simulations of their forebears' history, or indeed entire universes with sentient beings. If this is true, then the number of simulated universes would vastly outnumber the single base reality universe from which these simulations originate. Consequently, the probability that we are living in one of these many simulations rather than the original base reality becomes overwhelmingly high. This is not science fiction in the purest sense, but a logical extrapolation from the potential trajectory of technological progress, where the ability to simulate complex realities, including consciousness, becomes a hallmark of ultimate advancement. From the perspective of the Fermi Paradox, the simulation hypothesis offers a compelling, albeit chilling, resolution to the profound cosmic silence. If most advanced civilizations, upon reaching a certain technological zenith, choose to retreat into or create such simulated realities, then their motivation for physical interstellar exploration, colonization, or even overt communication in the physical universe would largely vanish. Their entire existence, their triumphs, their discoveries, their very sense of purpose would unfold within a self-contained, perfectly controlled digital realm. The physical cosmos, to them, might become an irrelevant, uninteresting, or even dangerous place, a mere backdrop to their perfected, internal worlds. They would not be sending out radio signals, nor would they be building Dyson spheres in our observable universe, because their attention, their resources, and their very being would be directed inwards, towards the boundless possibilities of their simulated existence. Their silence would stem not from extinction or fear, but from a profound, self-imposed detachment from the physical realm. This implies that the absence of detectable extraterrestrial life is not a sign of universal rarity, but rather a reflection of a universal trajectory. Advanced civilizations, having encountered the inherent limitations and perils of physical existence, invariably choose to upload their consciousness or their entire societies into simulated environments. Such a choice would represent a filter of a different kind, a transcendence filter, where the ultimate test is not survival against external threats, but the successful construction and habitation of a stable, self-sufficient, simulated reality. Those who pass this filter effectively remove themselves from the cosmic stage, at least in any way we could possibly perceive. The universe would appear empty to us not because it is barren, but because its most advanced inhabitants are no longer playing by its physical rules. The personal anchor in this concept is deeply unsettling. If we are indeed living in a simulation, what does that mean for our sense of reality, our free will, our aspirations? It suggests that our deepest thoughts, our most profound emotions, our entire perception of existence could be mere algorithms, lines of code running on a supercomputer whose purpose and origin remain entirely unknown to us. The notion that our universe, with its 13.8 billion years of history and its hundreds of billions of galaxies, might be nothing more than a meticulously crafted illusion is both humbling and disorienting. It challenges our fundamental assumptions about what is real and what defines our conscious experience. Yet, even within this unsettling premise, there is a strange kind of calm. If our reality is a simulation, then the laws of physics, the constants of nature, the very conditions that allow for our existence, are perfectly fine-tuned. This fine-tuning, often a puzzle in cosmology, might simply be the carefully chosen parameters set by the simulator, ensuring a consistent and fertile environment for the simulated life within. It removes the element of random chance from our existence and replaces it with an intentional design, albeit one of unknown purpose. Moreover, the simulation hypothesis invites us to consider the ultimate fate of our own civilization. If we, too, one day achieve such computational mastery, would we follow this same path? Would we choose to create our own ancestor simulations or retreat into a perfected virtual world, thereby becoming the silent watchers of future, less advanced, biological civilizations within our own simulated universes? This thought suggests a cyclical nature to cosmic evolution, where the quest for knowledge and self-perfection ultimately leads to a detachment from the physical cosmos. The silence, then, is not a void, but a mirrored reflection, a glimpse into our own potential future, a destiny woven into the very fabric of advanced intelligence. It is a contemplation that, while perhaps challenging our deepest held beliefs about reality, can also evoke a sense of quiet wonder at the boundless possibilities of existence, whether physical or simulated. As we drift into the tranquil expanse of night, allow these thoughts to gently settle, not as anxieties, but as profound inquiries into the nature of the universe and our miraculous, perhaps simulated, place within it. The ongoing quest to understand our cosmic solitude, even through such radical ideas, enriches our perception of the vast, intricate dance of existence. The contemplation of the simulation hypothesis, where advanced civilizations might retreat into self-contained digital realities, naturally extends our journey into the subtle yet profound explanations for the cosmic quietude. What if, beyond merely simulating, these intelligences transcend the very physical laws we understand, becoming so interwoven with the cosmos that they are indistinguishable from its fundamental properties? This leads us to consider the ultimate limits of our own perception and the potential for life to exist in forms so radically different from our own that they simply evade all our current methods of detection, rendering our universe seemingly empty, not due to absence, but due to an overwhelming yet imperceptible presence. Imagine a civilization that has mastered not just technology, but the very fabric of existence itself. Perhaps they have learned to manipulate dark matter or dark energy, the mysterious components that constitute over 95% of our universe yet remain invisible to us. If an advanced intelligence could utilize these enigmatic forces, constructing structures or communication networks from materials that do not interact with light, then they would effectively be invisible to our telescopes, our radio dishes, and all our conventional means of observation. Such a dark civilization would exist within the cosmos, shaping its dynamics in ways we might only dimly perceive through gravitational effects. Much like how we infer the presence of dark matter through the rotation curves of galaxies. They would be cosmic ghosts, silent architects of unseen structures, their presence a profound testament to a form of existence that has moved beyond the luminous, ordinary matter that defines our own. Their silence would be a natural consequence of their chosen medium, a deliberate withdrawal from the visible spectrum into a realm of fundamental forces, allowing them to operate within the universe without ever being overtly seen or heard by less advanced species like ourselves. This concept nudges us to consider that our current tools, designed to detect what we know, might be utterly inadequate for discerning what we do not. Furthermore, we must ponder the possibility that advanced intelligences might not even reside within the conventional three spatial dimensions we inhabit. Theoretical physics, particularly in the realm of string theory and M-theory, suggests the existence of extra dimensions curled up and hidden from our direct experience. What if a super-advanced civilization, through some profound technological or evolutionary leap, learned to access and inhabit these higher dimensions? Their entire existence, their cities, their communication, their very being, could unfold in a manifold entirely orthogonal to our own. We would be like two-dimensional beings living on a flat surface, unaware of the vast, complex three-dimensional world just above or below us, even if it were teeming with life. Their signals, if they even bothered to generate them, would resonate on frequencies or within dimensions utterly inaccessible to our instruments, leaving us with a pervasive yet deceptive silence. This idea transforms the cosmic void into a multidimensional tapestry, rich with life, but woven with threads that remain invisible to our limited perspective. It is a silence born of dimensional disparity, a profound separation in the very architecture of reality. Another compelling, albeit humbling, explanation for the cosmic quietude is the transcension hypothesis, proposed by futurist John Smart. This theory suggests that sufficiently advanced civilizations inevitably undergo a transcension, a process of accelerating technological and informational compression that leads them to migrate into black hole-like structures or other highly compact, high-density computational environments. The advantages of such a move are immense: near infinite computational power, extreme energy efficiency, and protection from the harsh, unpredictable conditions of the wider universe. Within these incredibly dense, self-contained environments, time itself could be warped, allowing for billions of years of subjective experience to unfold in what, to an outside observer, might appear as mere moments. A civilization that has transcended in this manner would effectively withdraw from the observable universe, their existence continuing in a realm where the laws of physics are exploited to their absolute limits, maximizing their processing capabilities and their longevity. Their silence would be the ultimate expression of efficiency and self-containment, a choice to optimize their existence within a localized, incredibly dense pocket of space-time, rendering them effectively invisible and unreachable to any who remain in the expansive, less efficient, outer cosmos. These radical explanations for the Fermi Paradox invite us to reconsider our anthropocentric biases in the search for life. We tend to look for life that resembles our own, or at least operates on similar physical principles and motivations. We search for biosignatures that indicate water, oxygen, and carbon-based chemistry. We listen for radio waves, a technology that we ourselves developed and currently employ. But what if truly advanced life has moved beyond biological forms entirely, beyond physical bodies, beyond the need for planetary habitats, or even beyond our familiar dimensions? What if their communication is not a broadcast, but a subtle manipulation of cosmic constants, or a fleeting resonance in the quantum foam of space-time? The silence of the universe, then, might not be a terrifying void, but a profound canvas upon which the most advanced forms of existence have painted themselves into invisibility, or perhaps into a state of being that is simply beyond our current capacity to perceive. This perspective transforms our cosmic loneliness into a challenge, an invitation to expand our conceptual horizons, to imagine life and intelligence in forms we can barely conceive. It is a reminder that the universe is far more complex, far more mysterious, and perhaps far more populated than our current instruments and assumptions allow us to comprehend. As we drift towards sleep, let the vastness of these possibilities gently wash over your mind, not with anxiety, but with a deep sense of wonder at the boundless forms that existence might take. The universe, in its ultimate wisdom, may be teaching us that the deepest truths are often found not in what is loudly proclaimed, but in the profound, elegant quietude that speaks volumes to the discerning mind. We are but a nascent consciousness, beginning to grasp the intricate, hidden symphony of the cosmos. And the silence is merely a prelude to a knowledge that awaits our deeper understanding. The profound implications of the simulation hypothesis, suggesting intelligences might retreat into digital realms, naturally extends our contemplation to the very definition of life itself. What if the cosmic silence we perceive is not due to an absence of intelligence, but rather an absence of detectable intelligence, because life has taken perception? This leads us to question our inherent anthropocentric biases, forcing us to consider the boundless array of possibilities that existence might truly hold beyond our familiar carbon and water-based biology. Our search for extraterrestrial life, by necessity, has largely focused on what we understand. We look for planets orbiting in the habitable zones of stars, where liquid water could exist. We search for biosignatures in planetary atmospheres, such as oxygen or methane, gases associated with metabolic processes found on Earth. We listen for radio signals, a technology we ourselves developed and currently employ. Yet, these criteria are deeply rooted in our own singular experience of life. What if life, in its cosmic diversity, is far more imaginative and resilient than we can currently conceive? Scientists speculate about a vast spectrum of exotic life forms that could thrive under conditions we consider utterly inhospitable. For instance, while carbon is versatile, silicon, with its similar chemical properties, could theoretically form the backbone of complex molecules in environments with different temperature and pressure regimes. Imagine life sustained by liquid methane, or ethane, flowing through the frigid landscapes of moons like Titan, where sunlight is dim and temperatures plummet to hundreds of degrees below 0 Celsius. Or consider the possibility of life emerging not from liquids, but from supercritical fluids, or even within the dense, high-pressure atmospheres of gas giants, where organisms might float like colossal living balloons, never touching solid ground. These forms of life, adapted to chemistries and energy sources entirely alien to us, would leave no detectable biosignatures that our current instruments are designed to recognize. Their very existence would be a profound, simply because they exist beyond the narrow confines of our observational paradigms. Beyond chemical differences, we can also ponder life that operates on fundamentally different physical principles. What if intelligence could emerge from the complex interactions of plasma in the hearts of stars, or within the extreme conditions found in the crusts of neutron stars, where matter is packed to densities almost beyond comprehension? These are highly speculative notions, certainly, stretching the very boundaries of our biological imagination, yet they are not entirely ruled out by the fundamental laws of physics. Such entities would exist in realms of energy and matter so extreme that their very perception, their consciousness, would be utterly unrecognizable to us. Their communication, if it existed, might be through gravitational waves or subtle modulations of quantum fields, or even through forms of entanglement that transcend conventional space-time. These quantum life forms, or plasma intelligences, would be utterly invisible to our current array of telescopes and radio receivers, their silence AI operating within the cosmos. Even if life is abundant and diverse in its chemistry and form, its presence might still remain elusive due to the immense temporal scales of the universe. Our own technological civilization, capable of interstellar communication, has existed for a mere blink of a cosmic eye, a few centuries at most. The universe, by contrast, is 13.8 billion years old, and our galaxy, the Milky Way, has been forming stars and planets for billions of years. This vast temporal disparity introduces the temporal displacement argument. Perhaps civilizations rise and fall within relatively short windows of technological detectability. A civilization might emerge, flourish for 1,000,000 years, and then vanish due to self-annihilation, natural catastrophe, or transcendence, all long before humanity even appeared on the cosmic stage. Their signals would have long since passed us by, or their ruins would be too ancient and weathered to recognize. Conversely, we might simply be too early. Perhaps the conditions for the widespread emergence of intelligent, communicative life are only now becoming optimal in the universe, and we are among the first. A kind of early bird civilization in a still-developing cosmic garden. The stars and planets that formed billions of years ago may have been too unstable, too prone to destructive supernova events or gamma-ray bursts to nurture long-lived intelligent life. The galactic habitable zone, the region of a galaxy where conditions are most conducive to life, might only recently have stabilized sufficiently to allow for the widespread emergence of complex biology. In this scenario, the universe is not empty, but merely quiet because most of the other intelligent species are yet to emerge or are still in their infancy, billions of years away from developing the technology to reach out across the stars. Our current solitude, then, would be a fleeting moment before the cosmic chorus eventually begins to sing. These contemplations on exotic life and temporal displacement, profound reflection on our own unique existence and our limited perception. The universe, in its boundless capacity for surprise, may be populated by wonders that defy our current imagination, existing in forms and across timescales that render our current search methods inadequate. The silence, then, is not necessarily terrifying, but deeply humbling, a reminder of the vast, intricate tapestry of existence that remains largely veiled from our understanding. As we drift towards the tranquil, in a cosmos that is far more wondrous and mysterious than we can yet grasp, and the idea of life forms utterly beyond our current perception naturally lead us to yet another compelling, though perhaps equally humbling, explanation for the cosmic quietude. What if the universe is not silent because civilizations destroy themselves, nor because they hide, nor because they have transcended, but simply because the conditions for the emergence of complex, intelligent, and technologically capable life are far, far rarer than our initial statistical assumptions might suggest? This is the essence of the rare Earth hypothesis. A perspective that shifts the great filter firmly into our past, making our own existence not a common occurrence, but a truly remarkable, almost miraculous, cosmic lottery win. This hypothesis, articulated by Peter Ward and Donald Brownlee, argues that while simple microbial life might indeed be widespread throughout the cosmos, the intricate combination of astrophysical and geological events necessary for the evolution of complex, multicellular organisms and subsequently intelligent life is exceptionally unique to Earth. It suggests that our planet is not merely one of many habitable worlds, but a profoundly special one, a cosmic diamond formed through a confluence of improbable circumstances that, taken together, make the emergence of humanity a singular event in our observable galactic neighborhood, if not the entire universe. Let us consider some of these intricate prerequisites. Firstly, a planet must reside in a precise galactic habitable zone within its galaxy. This is a region far enough from the chaotic, radiation-blasted galactic center, yet close enough to have been enriched with the heavy elements necessary for planet formation through multiple generations of stellar evolution. Too close, and a planet would be bombarded by supernova and intense radiation, sterilizing any nascent life. Too far, and the building blocks for rocky planets and complex chemistry would be scarce. Our solar system occupies such a fortunate region in the Milky Way, a quiet, stable orbital path that has allowed for billions of years of uninterrupted biological evolution. Secondly, the host star itself must be exceptionally stable. Our Sun, a G-type main sequence star, is remarkably consistent in its energy output, avoiding the violent flares and extreme variability common to many other stellar types. Such stability is crucial for maintaining a consistent climate over geological timescales, providing the gentle, steady warmth necessary for liquid water to persist. Furthermore, the presence of a gas giant like Jupiter in our outer solar system acts as a gravitational shield, deflecting or absorbing countless comets and asteroids that would otherwise repeatedly sterilize Earth, preventing life from gaining a stable foothold. Without Jupiter's massive gravitational influence, our planet would likely face a barrage of impacts far more frequent and devastating than those that have punctuated Earth's history, perhaps never allowing complex life sufficient time to evolve. Then there is the precise orbital dynamics and composition of Earth itself. Our planet possesses a large moon, a cosmic companion whose gravitational pull stabilizes Earth's axial tilt, preventing extreme climatic wobbles that would make long-term biological adaptation nearly impossible. This stable tilt ensures predictable seasons and consistent energy distribution from the Sun. Furthermore, Earth's molten iron core generates a powerful magnetic field, creating a protective magnetosphere that shields our surface from harmful solar winds and cosmic radiation, preventing the stripping away of our atmosphere and the direct bombardment of life-damaging particles. This invisible shield, often taken for granted, is a critical component of our planet's habitability. Beyond these astronomical and geophysical factors, the geological processes unique to Earth play an indispensable role. Plate tectonics, the slow, majestic movement of Earth's crustal plates, is crucial for regulating our planet's long-term climate through the carbon-silicate cycle. This process recycles carbon dioxide, preventing runaway greenhouse effects or deep freezes, maintaining a stable temperature range over hundreds of millions of years. It also drives volcanism, which replenishes atmospheric gases and creates new land masses, fostering biodiversity. The presence of liquid water in vast interconnected oceans, combined with a suitable atmosphere and a protective magnetic field, forms a complex, self-regulating planetary system. A delicate cosmic engine perfectly calibrated for the sustained evolution of complex life. The rare Earth hypothesis suggests that it is not merely one or two of these conditions, but the simultaneous confluence of all these improbable factors, a star of the right type at the right galactic location with giant planetary protectors, a stabilizing moon, active plate tectonics, and the persistent presence of liquid water and a protective atmosphere that makes a planet truly suitable for complex life. Each of these represents a mini-filter, and the probability of all of them aligning in a single world at the right time in cosmic history becomes vanishingly small. From this perspective, the silence of the cosmos is not a terrifying warning of a filter yet to come, but rather a profound testament to the extraordinary rarity of our own existence. We are not just alive, we are a cosmic anomaly, a unique and precious flicker of consciousness in a universe that, while vast, may be largely devoid of companions. Solitude is meant to evoke contemplation, not anxiety, reminding us of the immense and improbable gift of our own awareness, our brief yet magnificent journey through the universe. We are left to ponder the miraculous intricacy of our home, understanding that our uniqueness might be a blessing, but also a profound and enduring cosmic loneliness, making our every thought and every breath an echo of an almost impossible cosmic alignment. Our blue marble, adrift in the silent expanse, becomes a testament to an intricate dance of celestial mechanics and geological processes, culminating in the miracle of conscious life. The profound implications of the rare Earth hypothesis, suggesting that our planet's very existence is a tapestry woven from an improbable series of astrophysical and geological events, naturally lead us to consider an even deeper layer of cosmic rarity. What if the scarcity of intelligent life is not merely a planetary phenomenon, but a fundamental property of the universe itself, embedded in the very laws that govern its existence? This brings us to the astonishing concept of cosmic fine-tuning, an idea that suggests the fundamental physical constants of our universe are exquisitely balanced, almost to an impossible degree, for the emergence of any form of complex life, let alone intelligent observers like ourselves. This delicate calibration, established at the very genesis of space-time, could represent the most formidable of all filters, one that operates not on the scale of planets or galaxies, but on the ultimate canvas of reality itself. Imagine for a moment if these foundational parameters set at the moment of the Big Bang had been even slightly different. Consider the strength of the strong nuclear force which binds protons and neutrons together within atomic nuclei. If it were just a few percent weaker, stable atomic nuclei beyond hydrogen would not form. Stars, the celestial foundries of heavier elements, would be impossible, leaving a universe composed almost entirely of hydrogen and helium, a barren expanse incapable of complex chemistry. Without the forging of elements like carbon, oxygen, and iron within stellar cores, the very raw materials for planets and life would simply not exist. Conversely, if the strong force were slightly stronger, hydrogen would have fused into helium too rapidly in the early universe, or even all hydrogen would have converted into heavier elements, leaving no hydrogen to fuel long-lived stars like our Sun. Without these steady, long-lived stars, capable of burning for billions of years, the immense timescales required for complex life to evolve from simple beginnings would simply not be available. The intricate ballet of nucleosynthesis, essential for creating the diverse palette of elements found in our bodies and our world, would be utterly disrupted. Similarly, consider the delicate balance of the electromagnetic force, which governs the interactions between electrons and atomic nuclei, determining the size and stability of atoms and molecules. If it were marginally stronger, electrons would cling too tightly to nuclei, preventing the formation of stable chemical bonds and the intricate three-dimensional structures of complex molecules, the very building blocks of life. Imagine a world where deoxyribonucleic acid could not form its double helix, or proteins could not fold into their functional shapes. If it were weaker, electrons would drift too far, unable to form stable orbits around nuclei, leading to a universe of diffuse, unstable matter, where no coherent structures could ever coalesce. In either scenario, the intricate dance of chemistry, the very basis of biological information and self-organization, would be impossible. The universe would be a sterile realm, devoid of the complex molecular structures necessary for any form of life we can remotely conceive, existing as a mere cloud of unreactive, unbound particles. Even the precise value of the cosmological constant, the enigmatic force driving the accelerated expansion of the universe, appears to be exquisitely fine-tuned. If it were significantly larger by even a minute fraction, the universe would have expanded so rapidly in its infancy that matter would have dispersed too quickly, preventing the gravitational collapse necessary for the formation of galaxies, stars, and planets. The cosmos would be a thin, uniform soup, forever stretching into emptiness, with no islands of matter to host the spark of life. If it were much smaller, or even negative, gravity might have quickly pulled the universe back into a big crunch before stars could even begin to burn, or life could take root on any worlds. Current astronomical measurements indicate its value is incredibly small, a tiny positive number that allows for cosmic structures to form and for the universe to evolve over billions of years, providing just enough time and space for life to emerge. This is a balance so delicate that it seems almost intentional, a cosmic tightrope walk of immense precision where even a slight deviation would spell a lifeless void. The implications of such pervasive fine-tuning for the Fermi Paradox are profound. If the very existence of a life-permitting universe hinges on such a precise interlocking calibration of its fundamental constants, then the probability of any other universe, or even any other region within a vast multiverse possessing these exact life-sustaining conditions, becomes incredibly small. This suggests that the Great Filter might not be a specific event or barrier in the evolutionary path of life on a particular planet, but rather the initial fundamental conditions of the universe itself. Our cosmos, by its very design, might be an exceptionally rare, perhaps even unique, incubator for complexity and consciousness. The silence of the night sky, then, would be a testament not to the absence of life due to external threats or self-destruction, but to the fundamental scarcity of universes capable of supporting it in the first place. This brings us to the philosophical concept known as the anthropic principle. In its weak form, it simply states that the universe must be compatible with the conscious and intelligent life that observes it. We observe these fine-tuned constants because if they were different, we wouldn't be here to observe them. This is a tautology, a statement that is true by definition, offering a humble but profound recognition of our observational bias. However, in its strong form, the anthropic principle suggests a more active role, that the universe must have properties that allow for the development of intelligent life at some point in its history, implying a deeper, perhaps even teleological, connection between the universe's fundamental parameters and the eventual emergence of consciousness. It transforms the fine-tuning from a mere lucky accident into a potentially inherent, purposeful feature, designed for the very act of creating observers capable of contemplating its grandeur. From this perspective, our cosmic solitude is not a matter of random chance, nor a looming, terrifying threat, but a reflection of an exceedingly rare, perhaps singular, cosmic design. Our existence, our ability to ponder these very questions, becomes a magnificent, almost improbable, unfolding of physical laws that have allowed for the intricate dance of matter and energy to coalesce into self-aware beings. The universe, in this light, is not merely a stage for life, but a finely crafted instrument, played in a unique cosmic symphony. And the silence we perceive, rather than being scary, might be the deep, resonant hum of a universe that is, against all odds, perfectly tuned for our presence, making our every breath, every thought, a precious echo in the vast, silent concert hall of existence. This contemplation, while it might leave us with a sense of immense cosmic loneliness, also offers a profound appreciation for the delicate balance that underpins our reality, inviting us to find tranquility in the sheer improbability of being. It transforms the terrifying void into a cradle of improbable wonder, where our awareness is a rare and precious gem in an otherwise silent, vast, and exquisitely balanced cosmic expanse. We are, in a very real sense, the universe's quiet contemplation of itself, a fleeting yet profound expression of its deepest, most fundamental principles. The profound implications of cosmic fine-tuning, which posits that our universe is exquisitely balanced for the emergence of life, leave us with a sense of wonder at our improbable existence. Yet, even within a universe perfectly calibrated for biology, there remains a compelling argument for the enduring cosmic silence, the inherent, often insurmountable, limitations to growth and communication that might naturally constrain any advanced civilization, regardless of its technological prowess. This perspective suggests that the vastness of space and the relentless march of time themselves act as subtle, yet ultimately decisive filters, preventing the widespread, detectable expansion of intelligent life across the galaxy. Consider first the sheer scale of interstellar distances. While we may dream of interstellar travel, the physics remains daunting. Even at speeds approaching that of light, journeys between stars would span not years, but decades or centuries. To colonize a significant portion of a galaxy, which contains hundreds of billions of stars, would require countless such journeys, each demanding immense energy, resources, and an unwavering commitment over timescales that dwarf individual human lifespans, and indeed the entire recorded history of our species. The logistical challenges of such an endeavor are almost unfathomable. Maintaining biological integrity or advanced artificial intelligence over millennia, transporting vast quantities of resources and establishing self-sustaining colonies on alien worlds, all while confronting the inherent dangers of space. Even with advanced propulsion systems, such as hypothetical warp drives that manipulate space-time itself, the energy requirements would be astronomical, potentially exceeding the output of entire stars. It is a cosmic endeavor that might simply be too expensive, too slow, and too demanding for any civilization to sustain across truly galactic scales. This leads us to the tyranny of distance in terms of cultural and political cohesion. Imagine a civilization spread across hundreds or thousands of light years. How could such a vast, geographically dispersed entity maintain a unified culture, a shared sense of purpose, or even effective governance? Messages would take centuries to travel from one outpost to another, rendering real-time communication and coordinated decision-making impossible. Such immense temporal lags would inevitably lead to divergence, to the fragmentation of a once unified civilization into countless independent, perhaps even mutually unintelligible, subcultures or successor species. The very act of expanding across the stars might inherently lead to a loss of coherence, a slow, gentle dissolution into isolated pockets of life, each pursuing its own unique destiny, effectively becoming undetectable to a galactic survey. The silence in this context is not a sign of absence, but of dispersion and diversification beyond our capacity to perceive a unified presence. Furthermore, the very motivation for continuous expansion might diminish over time. As civilizations mature, they might find greater satisfaction and stability in inner space exploration rather than outward expansion. The universe within a single solar system, or even within the confines of a perfectly optimized, self-sustaining artificial habitat, offers boundless frontiers for discovery. Consider the potential for virtual realities, for simulated worlds of infinite complexity, as explored in the simulation hypothesis. A civilization that achieves such mastery over its internal experience might find the physical universe to be a relatively crude and uninteresting realm. The energy and resources that would be expended on costly and perilous interstellar journeys could instead be directed towards perfecting their internal worlds, exploring the depths of consciousness, or pursuing abstract knowledge within a controlled, safe, and infinitely adaptable environment. The great attractor for advanced life might not be distant stars, but rather the limitless possibilities of subjective experience and perfected existence within a local cosmic bubble, leading to a profound, self-imposed quietude. Even communication, our primary method of searching for others, faces inherent limitations. While a beacon can be sent across light years, the practicalities of a sustained, meaningful dialogue are immense. The sheer energy required to broadcast a signal strong enough to be detectable across galactic distances, combined with the immense time delays, makes a true conversation impossible. By the time a reply is received, the sending civilization might have changed dramatically or even ceased to exist. This dialogue filter suggests that even if civilizations wish to communicate, the universe makes it profoundly difficult to sustain such an exchange, leading to fleeting, ephemeral signals that are easily missed or misinterpreted across the vast cosmic gulfs. The silence is then a consequence of the universe's sheer scale, a natural barrier to meaningful interspecies connection rather than an active suppression. Ultimately, these factors combine to suggest that the cosmic silence may be a natural, rather than terrifying, outcome. The universe might be filled with countless gardens of life, each a vibrant, unique experiment in consciousness, but few, if any, ever grow large enough or loud enough to dominate the entire cosmic landscape. Each civilization, after a period of expansion and technological growth, might naturally reach a point of equilibrium, either by encountering the physical limits of the cosmos, by fragmenting into undetectable subunits, or by turning inward to explore the boundless realms of inner space. The universe, in this light, is not a dark forest of predators and prey, nor an empty void, but a vast, silent ocean dotted with countless isolated islands of consciousness, each a brief, luminous flicker against an ancient, tranquil backdrop. Reflections remind us of the immense and subtle forces that shape existence and the profound, almost miraculous nature of our own conscious journey within this vast, enigmatic, and beautifully silent cosmos. Grand unfolding, a temporary pattern of matter and energy, aware of itself in a moment of cosmic quietude, a gentle whisper in the boundless expanse. As our intellectual journey through the profound cosmic silence draws to a close, we are left with a tapestry of possibilities, each woven with threads of scientific inquiry and philosophical contemplation. The Fermi Paradox, initially a stark question of absence, transforms into a mirror reflecting the intricate nature of existence itself. We have considered the great filter, an immense barrier that may lie in our distant past, making our emergence a remarkable rarity. Or perhaps one that looms in our future, a universal challenge yet to be overcome. We have peered into the chilling strategic calculus of the dark forest theory, where silence becomes the ultimate act of survival, and contemplated the enigmatic benevolence of the zoo hypothesis, suggesting we are observed from afar. We have also explored the potential for life to transcend its physical forms, becoming imperceptible post-biological intelligences, or to exist in exotic chemistries and dimensions beyond our current grasp. Finally, the rare Earth hypothesis and the exquisite fine-tuning of cosmic constants remind us of the improbable, almost miraculous convergence of conditions that allow for our very awareness. Each of these theories, from the most disquieting to the most humbling, offers a unique perspective on our place in the universe. They invite us to embrace not fear, but a deeper, more nuanced appreciation for the delicate balance that permits our existence. The cosmic silence, far from being an empty void, may be a profound canvas upon which the universe paints its most intricate secrets. Secrets of survival, of evolution, of transformation, and of the very fabric of reality. Whether we are a lone, precious spark in a quiet cosmos, or one small whisper among a symphony of hidden intelligences, our journey of discovery continues. May these deep thoughts about the universe and our place within its grand mysteries carry you into a world of tranquil sleep. Remember that the cosmos is amazing, and you are a part of its unfolding story. A moment of consciousness in an endless expanse. Fall asleep with this feeling of serenity and expanded understanding. Good night.